When astronomers first spotted Oumuamua in 2017, it shook the scientific world. It was the very first known visitor from beyond our solar system, an object that slipped through the darkness like a cosmic messenger. It left more questions than answers in its wake. Its shape was bizarre, its movements were puzzling, and its fleeting passage stirred debates that continue today. But just when we thought nothing could rival that mystery, another interstellar traveler appeared, 3 Atlas. Unlike Oumuamua, this new arrival offers a chance not just to speculate, but to truly study. To study what these wandering bodies from other star systems are made of. Where Oumuamua left us in suspense, 3 Atlas promises revelations. And that changes everything. Could this be the missing piece we've been waiting for? But before we start this journey into the unknown, let us know where in the world you're watching from and what time it is for you right now. And get ready to explore the mysterious new visitor, 3 Atlas. Astronomers spend many long nights staring at computer screens that to most people would look dull and lifeless. All that appears are tiny dots of light scattered across an endless sea of black. To the untrained eye, those dots look like nothing more than random white specks sprayed onto a dark canvas. But to astronomers, every dot has meaning. Each one carries a story older than human history. Some of those lights are stars that have been burning for billions of years. They have been holding steady in the same spot since the birth of galaxies. Others are distant planets, moons, or even lonely asteroids. They are quietly reflecting sunlight as they drift through the cold emptiness. Most of the time, these dots behave exactly as expected. They move in steady patterns guided by the unshakable laws of gravity, laws that have ruled the universe since its very beginning. On most nights, nothing unusual happens. Stars remain in their ancient places. Planets trace their familiar orbits around the sun, and even wild-looking comets or asteroids ultimately keep to paths carved for them by gravity. To astronomers, it often feels as though the universe is a grand theatre. Every celestial actor, the stars, the planets, the comets, knows its lines and follows the script without error. But then came a night when the universe itself decided to surprise us. On the 19th of October, in the year 2017, something strange broke the cosmic routine. Something appeared in the sky that did not belong there at all. The discovery began quietly, with a single image captured by the Pan-STARRS telescope in Hawaii. This powerful instrument sits high atop the summit of Haleakala. Its gaze constantly sweeps the heavens for moving objects. Objects like asteroids that one day might pose a danger to Earth. That night, the telescope recorded what looked at first like just another unremarkable dot of light. But when astronomers compared it with the next images, their pulses quickened. This dot was moving in a way that no local object ever moved. At first, disbelief ruled the room. Many astronomers thought it had to be an error, a miscalculation by the computer. But more data arrived, and the truth became undeniable. This was no ordinary comet or asteroid circling the sun. Instead, it followed a hyperbolic path, a sharp arc, showing that it was not bound to the sun's gravity at all. It was not born in our solar system. It was a visitor, an interstellar traveler. It had crossed the vast gulf between stars to appear just for a moment in our sky. Calculations soon revealed its astonishing speed. It was racing at 26 kilometers every second relative to the sun. That is nearly 94,000 kilometers in a single hour. An impossible pace for any object formed in our neighborhood of space. In that instant, humanity realized the universe had sent us something entirely new. News spread quickly, and the scientific world erupted into controlled chaos. Researchers everywhere scrambled to request emergency telescope time. They were desperate to catch a glimpse before the object slipped back into the darkness forever. Within hours, observatories from Hawaii to Chile turned their eyes toward the mysterious visitor. Observatories from the mountains of Europe to the deserts of North America. Even outside the scientific community, excitement exploded. Social media buzzed with speculation. News anchors across the world tried and often stumbled to pronounce its Hawaiian name, Oumuamua. In Hawaiian, the word means scout or messenger from afar arriving first. The name seemed perfect, as though this object had been sent across the cosmos to deliver a hidden message. At first, astronomers imagined it must look like the many comets and asteroids already known, things like rough, lumpy spheres of rock or ice. But something quickly stood out. As Oumuamua spun through space, its brightness changed in a dramatic way by nearly 10 times. No ordinary asteroid behaves like that. The only explanation was that it was not round at all. It had to be extremely stretched out, unlike anything ever observed before. The best guess was that it was shaped like a cigar, perhaps 800 meters long but only 80 meters wide. It was tumbling end over end like a baton tossed by an invisible hand. To put that into perspective, its length was about the size of 8 football fields, but its width was only that of a single one. And still the mysteries deepened. Its surface reflected sunlight in unusual ways. Some astronomers thought it might be coated in a shiny crust. Others suggested it could be made of some exotic material we'd never seen before. And then came the boldest whispers, the daring thought that perhaps it was not natural at all. More puzzles followed as Oumuamua sped past the sun. Most comets, when warmed by sunlight, release jets of gas that act like tiny rocket engines. These jets push them slightly off course, but when astronomers looked for such jets, they saw none. Yet somehow Oumuamua was accelerating as though something invisible was nudging it forward. How could that be? Dr. Robert Werrick, the astronomer who first noticed the object, later described the shock of that night. "You look at the data and you think the computer made an error," he said. "Objects just don't move like this in our solar system." But the computer was not wrong. The universe had handed us a mystery unlike any we had faced before, and so the questions began. Was Oumuamua nothing more than a shard of rock flung out from another star system billions of years ago? Was it wandering through interstellar space until it finally passed through ours? Or was it something far more extraordinary, a piece of technology built by a civilization beyond our own? For the first time in human history, we were forced to confront a possibility. The possibility that we had just glimpsed a visitor from the stars. Not just a traveler, but perhaps even a messenger. Most scientists lean toward ordinary natural explanations. After all, the universe has its own ways of creating wanderers. Gravity, the invisible force that rules the motion of planets and stars, can act like a cosmic slingshot. Around giant planets, small bodies like comets and asteroids can be flung out of their home systems with incredible speed. It was not hard to imagine that Oumuamua was simply one of these. A lonely traveler cast adrift into the endless dark. And that we had just been fortunate enough to spot it. Yet not everyone was satisfied with the idea of simple luck. Humanity has been scanning the skies with powerful telescopes for less than 1 single century. A blink of an eye in cosmic time. The odds of witnessing such a rare visitor during that narrow window seemed impossibly slim, unless interstellar objects were far more common than we had dared to believe. This realization shook astronomy to its core. Suddenly, research programs around the world shifted their priorities. Scientists began inventing new methods to detect strange objects that moved along interstellar paths. Funding, once nearly impossible to secure for such wild ideas, started to flow more easily. Oumuamua had not only sparked wonder, it had rewritten the rules of what astronomers considered possible. But our time with this mysterious object was heartbreakingly short. By the moment it was first noticed, Oumuamua had already swung past the sun. It was racing back out into the deep, We had only a handful of weeks to study it before it faded away, beyond the reach of even our most powerful instruments. Still, in that fleeting window, what we discovered both enlightened us and unsettled us. We learned that it was strangely elongated, tumbling in unpredictable ways, and it was accelerating as though something unseen was pushing it. We saw that its surface reflected sunlight in odd patterns unlike anything we had ever studied. We confirmed that it did not belong to our star system and followed no orbit familiar to us, but so much remained hidden. We never saw its true shape in sharp detail. We never uncovered what it was made of. We never discovered whether it was a natural fragment of some ancient world or an artificial messenger from an unknown intelligence. It came offered us just enough to stir our imagination and then was gone. As it slipped into the darkness, Oumuamua sailed toward the constellation Pegasus. It was moving at nearly 38 kilometers every second. No spacecraft humanity had ever built could hope to catch it. Our fastest machines were like crawling snails compared to its astonishing pace. All we could do was watch as it left us behind. It trailed questions that may never be fully answered, and yet in its passing it left us with a profound truth. The space between the stars is not empty. It is alive with wanderers, some born of natural processes, and perhaps some carrying designs we cannot yet comprehend. For thousands of years, people looked at the night sky and believed we were cut off, isolated within our solar system. Stars glittered at unreachable distances. Moons, planets, and comets seemed to belong solely to our sun. The idea of something visiting from another star was considered pure fantasy. But in October of the year 2017, that fantasy became a reality. Oumuamua tore away the veil of certainty. It revealed that the galaxy is not a sealed vault but a network of invisible highways. Highways along which objects travel for unimaginable stretches of time and distance. Some of these voyages may be shards of broken worlds hurled outward by violent cosmic collisions. Others may be frozen messengers carrying the ancient chemistry of long-dead planetary systems, and perhaps, though proof still escapes us, some may even be crafted. Oumuamua was only the first act. In the year 2019, another interstellar traveler appeared, Comet Borisov. This one looked more familiar with its glowing tail of gas and dust. It was like the comets we had studied for centuries. Its arrival confirmed what Oumuamua had whispered. Our solar system is not a lonely bubble but part of a greater galactic current, a current flowing with countless wanderers. If two such visitors could arrive within only a couple of years, then there must be many more passing by, just waiting for us to notice them. That is why astronomers are building new eyes for the sky. The Vera C. Rubin Observatory, soon to begin its great survey of the heavens, will scan with unprecedented sensitivity. It may soon reveal dozens, perhaps even hundreds of interstellar objects every single year. And among those, what will we discover? Some may puzzle us as Oumuamua did. Others may astonish us with shapes, colors, and behaviors we never imagined. The possibilities stretch far beyond the limits of our current understanding. One day when we look back, the story of Oumuamua may be remembered as a turning point. It was the first moment when humanity knew with certainty that visitors from the wider galaxy could and did enter our neighborhood. It was the first proof that the dark between the stars is not empty but alive with travelers. Astronomers, dreamers, and philosophers continue to wonder, was it only a rock, or was it a messenger carrying a secret we were not yet ready to understand? Oumuamua was not only a mystery in itself, it also became connected to one of the most fascinating ideas. An idea about how life may have begun and spread throughout the universe. This idea is known as panspermia, and it carries with it a bold suggestion. Life is not limited to our Earth. Instead, it might be scattered across the entire cosmos, traveling like tiny stowaways between planets, moons, and even star systems. At the heart of panspermia is a striking thought. Perhaps life did not even begin on Earth at all. According to this theory, the earliest life forms could have been born elsewhere and then carried here. Tiny, almost invisible organisms such as microbes or spores. Once they reached Earth, they might have multiplied, evolved, and eventually given rise to the incredible variety of life we see. Plants, animals, and humans. These little travelers could have found their way across the galaxy by clinging to specks of cosmic dust, or by hiding inside meteoroids, asteroids, and comets, or even though unintentionally hitching rides aboard spacecraft. What makes panspermia especially intriguing is that it does not try to explain how life itself first came into being. Instead, it focuses on how life, once it existed somewhere, could spread like seeds across the great emptiness of space. Scientists have imagined several versions of this process. Some suggest radiopanspermia, in which microbes are blown through this galaxy by starlight. Others imagine lithopanspermia, where rocks blasted off one world by a massive collision carry living stowaways to another. Still, others propose directed panspermia, the possibility that intelligent beings may have deliberately sent life out into space, life sent out to seed other planets. But in every case, the central idea is the same. Life is tough enough to survive the harshness of space and travel between worlds, perhaps even between whole solar systems. One of the most dramatic ways this might happen is through planetary collisions. Picture a thriving world, perhaps covered with oceans and microbes, being struck by a giant asteroid or comet. The impact would fling fragments of rock high into space. If living microbes were sealed within those fragments, some might survive. They could drift silently through the void for thousands or even millions of years until they crash onto another planet. If that new world had the right conditions, liquid, water, warmth, and nutrients, those humble passengers could awaken. They could multiply and start a whole new story of life. Of course, many scientists remain cautious about this idea. Panspermia, while exciting, does not truly solve the greatest mystery where life originally came from. It simply moves the question to another planet or another star system. Another difficulty is testing the idea. It is hard to prove with experiments because we cannot easily watch life leap from one world to another. For these reasons, panspermia has often remained on the outer edges of scientific debate, an intriguing possibility, but not the main explanation. Still, the idea refuses to fade. Some researchers have even built mathematical models showing how life could naturally move from one planet to another within a star system. Others point to meteorites that fall to Earth containing organic molecules, the raw materials of life. While these do not prove panspermia, they keep the discussion alive. Throughout history, the idea has also been linked to strange claims and hoaxes, especially after unusual meteorite falls. A more widely accepted cousin of the theory is called pseudopanspermia. This idea suggests that while entire living cells may not have traveled through space, the building blocks of life could have. Molecules such as amino acids could have formed among the stars and then landed on planets like Earth, where they sparked the first steps toward life. The thought that life might come from the heavens is far from new. As early as the 5th century before the Common Era, the Greek philosopher Anaxagoras declared that the universe was filled with life, and that seeds from space had fallen onto Earth to begin the living world we know. The modern version of panspermia, however, did not take shape until much later. The word panspermia itself was introduced in the year 1903 by the Swedish scientist Svante Arrhenius. Even earlier, during the 1860s, several famous scientists began exploring the idea in a more serious way. Scientists including the British astronomer Sir Fred Hoyle and the physicist Chandra Wickramasinghe. The 1860s were a turning point for science. 3 major discoveries forced researchers to rethink the mystery of life's beginnings: the Kant-Laplace nebula theory, This proposed that our solar system was born from a swirling cloud of gas and dust. It also suggested that early Earth was far too hot and violent for life to appear immediately. This raised the question of when and where life could have begun. Charles Darwin's theory of evolution. In his groundbreaking book On the Origin of Species, published in 1859, Darwin explained how species change over time. Yet he avoided answering how the very first life began. Louis Pasteur and John Tyndall's experiments. These scientists put an end to the old idea of spontaneous generation, the belief that life could just pop out of non-living matter. Their experiments showed that life always seems to come from pre-existing life. Together, these discoveries created a puzzle. If life cannot simply appear from nothing, and if Earth was once too hostile for it, then how did it begin here? Some argued for abiogenesis, the idea that life slowly emerged on Earth from simple chemicals. Others looked outward, believing that life must have arrived from the skies, a revival of panspermia. In the year 1871, the famous physicist Lord Kelvin offered an imaginative vision. Just as seeds drift on the wind, he suggested life might be carried through the cosmos on meteorites. A single space rock harboring microbes could crash onto Earth and release living passengers, starting life anew. Lord Kelvin also believed in something called philosophical uniformitarianism, the principle that the same natural laws apply everywhere in the universe. Just as matter cannot be created or destroyed, he argued, life must always come from life. But not everyone agreed. The German scientist Johann Zollner objected. He pointed out that organisms sealed in meteorites would almost certainly burn up while plunging through Earth's atmosphere. They would be destroyed by searing heat before they could reach the ground. To him, panspermia seemed nearly impossible. And yet, despite the doubts the idea has endured, while most scientists today lean toward abiogenesis, the slow birth of life from Earth's own chemistry, panspermia, continues to spark curiosity. The search for tiny life forms like microbes on Mars and on icy moons such as Europa and Enceladus is not only about finding life elsewhere, it is also about answering a deeper question. Could life have once existed far away and then somehow traveled here to Earth? If scientists ever discover even the smallest trace of living organisms beyond our planet, it could serve as powerful evidence. Powerful evidence for an idea known as panspermia. Until that day arrives, this idea remains one of the most captivating mysteries of science, one that makes us wonder where we truly came from and whether we are truly alone in the vast universe. Centuries ago, scientists argued passionately about how life first began on Earth. Among the loudest voices in this debate was a Swedish scientist named Svante Arrhenius. He disagreed strongly with the belief that life could simply appear out of lifeless matter. At the time, no one had any solid proof from experiments to support that possibility. Instead, Arrhenius proposed something far more daring, that life had always existed somewhere in the endless universe, and that it had traveled across space to finally take root on Earth. Arrhenius devoted himself to working out how tiny living forms, such as spores of bacteria, might actually travel between planets. Around this time, scientists had discovered something remarkable. Light from the sun does not only shine and warm, but also pushes. Sunlight exerts a very gentle yet steady pressure on objects. Building on this discovery, Arrhenius suggested that microscopic life forms could ride on beams of sunlight, like invisible passengers drifting across space from one world to another. This explanation gave the panspermia theory its first possible mechanism for how life could spread between planets. Yet not everyone was convinced. Many scientists wondered whether fragile spores could possibly survive the freezing cold, deadly radiation and endless emptiness of space, survive for millions of years. The idea also faced another serious obstacle. It was almost impossible to test in a laboratory experiment. That difficulty remains to this very day. Still, the theory did not fade away. In the 20th century, it found strong supporters in two bold thinkers, Fred Hoyle and Chandra Wickramasinghe. They believed life might not have originated on Earth at all for two main reasons. First, the conditions for life's birth may have been more favorable in other corners of the cosmos. Second, life on Earth seemed to carry certain puzzling features that were hard to explain if it had begun here alone. Hoyle especially studied the way starlight passed through massive clouds of interstellar dust. To his surprise, he found patterns suggesting the presence of organic molecules, the raw chemical ingredients of life. He proposed that these molecules might have taken part in a natural process that created life, but not here on Earth. Instead, he pointed to comets' giant icy bodies rich in organic material as the most likely cradles of this process. Even more daring was another idea they introduced. Hoyle and Wickramasinghe argued that viruses drifting through space might have shaped the history of life on Earth. According to them, comets passing close to our planet could have showered it with viral material. This would add new genetic information that changed the course of evolution. In fact, during a lecture at Oxford University on January 16th, in 1978, Hoyle even claimed something shocking. Certain devastating epidemics in human history seemed to line up with times when comets had passed nearby. This suggestion shocked many scientists and was fiercely criticized, especially by biologists who saw little evidence to support it. By the 1970s, the growth of space exploration opened new doors. Space probes and telescopes began collecting data that might someday test the panspermia idea. Even though the theory has never been fully proven, it continues to be explored through computer models and scientific debate. Its survival through so many decades shows how compelling and enduring the mystery remains. One branch of this theory, known as lithopanspermia, offers another possible method for life to spread. According to this version, living material could hitch a ride inside a meteorite. When an asteroid smashes into a planet, the force can blast pieces of rock into space. If those rocks contain tiny spores or even seeds, they might drift through space until colliding with another world. If the spores survived the journey and the fiery entry through the new planet's atmosphere, they could possibly take root and spread. Some scientists have also suggested that certain meteorites might even create little havens for life inside them. Radioactive elements within these rocks can generate heat-melting ice and creating tiny pockets of liquid water. Since water and energy are two of the key requirements for life, these rocky travelers could briefly become miniature worlds of their own. Indeed, some meteorites that have fallen to Earth contain signs that liquid water once existed inside them. With countless rocks drifting through our solar system, it is not impossible that many of them once carried microscopic life forms, and perhaps one such rock delivered the first seeds of life to Earth. Plants too have entered this discussion. Some seeds produced by plants are astonishingly tough. They can survive freezing cold, the vacuum of space, and even deadly blasts of ultraviolet light. While such seeds are not thought to form in space, it is possible they could be blasted off one world and survive the long journey to another. Even if battered and damaged, a seed might still sprout in a fresh environment. What makes this even more intriguing is that certain plant cells can repair themselves after being harmed. This raises the possibility that fragments of plants, not just whole seeds, might help spread life. In addition, many plant cells contain tiny symbiotic organisms living inside them. If such cells landed on a new planet, they might influence its ecosystems in unexpected ways. Scientists remain divided on whether seeds or spores could truly survive the long, dangerous voyage through space, and survive the fiery plunge into another planet's atmosphere. Yet, despite all the doubts, the idea of panspermia continues to spark curiosity. One of the most fascinating ideas in science is that life might not be trapped on just one planet. Instead, it could travel across the universe, hopping from world to world. This idea is called panspermia, a word that literally means seeds everywhere. It suggests that life is like a cosmic traveler scattering its seeds throughout the stars, waiting for the right places to take root and grow. Now, there are many possible ways this could happen. One surprising possibility is that humans themselves may already be unknowingly spreading life. Modern spacecraft built in giant laboratories on Earth are carefully cleaned so they do not carry contamination. But some microorganisms are so tough that they can survive even the most extreme sterilization procedures. One such microbe is called Tersicoccus phoenicis, and it has shown remarkable resistance to cleaning techniques used during spacecraft assembly. This means that even though space agencies take enormous care, there is always the chance that tiny stowaways could sneak aboard a probe. Once launched into the heavens, these invisible passengers could find themselves landing on distant planets or moons, carrying earthly life to alien worlds. Scientists divide panspermia into two major types. The first is interplanetary panspermia, which is the idea that life can travel between planets in the same solar system, perhaps from Mars to Earth or vice versa. The second is interstellar panspermia, which is a much grander idea. The idea that life might cross the gulf between completely different star systems moving across light years of space. Within these ideas, several possible methods have been proposed. More than 120 years ago, in 1903, a Swedish scientist introduced the concept of radiopanspermia. Svante Arrhenius suggested that the pressure of starlight itself can still push on objects, although light has no weight. If tiny life forms were floating in space, the gentle but steady push of radiation could carry them across the cosmos. Life forms, such as bacterial spores, smaller than 1.5 micrometers. At first, this sounded promising, but other scientists, such as Iosef Shklovsky and Carl Sagan, pointed out a huge problem. Space is not a friendly place. It is filled with deadly, ultraviolet radiation, powerful X-rays, and streams of high-energy particles. Any unprotected microbe drifting in the open void would be destroyed in seconds. Even if billions of spores were launched into space, the overwhelming majority would be annihilated. Still, supporters of the idea argued that if even a few survived, they might eventually reach a new planet, even if it took as long as 1 million years. To test these ideas, scientists ran real experiments in orbit. Space missions with names like ERA, Biopen, Exostack, and Expose carried bacterial spores into space. When left, unprotected bacteria, such as Bacillus subtilis, were destroyed in just a few seconds. But when shielded inside, materials like meteorite dust or clay, some of them survived. They survived not only for days, but for as long as 6 years. This shows that protection is the key. A microbe cannot survive space by drifting naked. But if it is buried inside rock or dust, its chances improve dramatically. Calculation suggests that for a microbe to truly withstand cosmic radiation, it would need to be inside a rock, at least 1 full meter wide. Without such protection, radiation would shatter the delicate molecules of DNA and RNA that make life possible. The vacuum of space itself also adds to the danger, tearing apart unprotected cells. Because of this, the idea of radiopanspermia seems extremely unlikely. Life drifting freely through space, pushed only by starlight. Another idea which many scientists find more convincing is called lithopanspermia. This theory suggests that life could hitch a ride inside rocks blasted off a planet's surface during a giant impact. For example, when a massive asteroid strikes a planet, the force of the collision can send chunks of rock flying into space. If microbes were hidden inside those rocks, they could potentially survive the violent launch. They could float through space for millions of years and eventually crash land on another planet. But the journey is full of dangers. The first challenge is surviving the violent ejection from a planet. When rocks are hurled into space by a colossal impact, they endure enormous pressures. Pressures ranging between 5 and 55 billion pascals, accelerations of up to 3 million meters per second squared, and temperatures that can soar from just 1 degree above absolute zero to more than 1,000 degrees Kelvin. Yet astonishingly, laboratory studies and Martian meteorites show that some microorganisms could survive even these brutal forces. The next challenge is the long voyage through the harsh emptiness of space. Bacteria in orbit have been tested by experiments simulating space conditions. Some microbes form protective biofilms, slimy layers that shield them from radiation. Others, known as extremophiles, are already adapted to survive boiling heat, freezing cold, or intense radiation. These tough survivors have shown that life is far more resilient than we once believed. Finally, there is the last and most dangerous hurdle: re-entry into a planet's atmosphere. When a rock plunges toward a planet, it becomes a fiery meteor. It heats up to temperatures that could kill any life trapped inside. To study this, scientists placed spores of Bacillus subtilis on granite rocks and launched them into space on a 2-stage Orion rocket. When the rocks came blazing back through Earth's atmosphere, the spores on the side survived. Those on the front, which reached 145 degrees Celsius, were completely destroyed. This shows that microbes buried deep within a rock stand a far better chance of surviving than those exposed on the surface. All of this paints a thrilling picture. While the theory of radiopanspermia struggles with the dangers of radiation, lithopanspermia remains a real possibility. Life traveling hidden inside rocks. If true, it means that the story of life on Earth may not have started here at all. Perhaps our earliest ancestors were cosmic voyagers, seeds of life carried across the stars, seeds who found a safe harbor on this blue planet billions of years ago. And perhaps even now we are unknowingly returning the favor, sending earthly microbes out into the cosmos aboard our own spacecraft, ready to begin new stories on distant worlds. Lithopanspermia is the idea that life can travel from one world to another, riding on rocks blasted into space. Most often scientists discuss this in terms of nearby planets in our own solar system. For example, the possibility that life might have jumped between Earth and Mars. But some thinkers take the idea even further. They suggest that this process could also happen on a far greater scale across the gulf between different stars. Take, for example, the planetary system of the star known as TRAPPIST-1. This star has several Earth-sized planets circling very close together, almost like beads strung tightly on a necklace. A recent scientific study suggested that lithopanspermia could actually be much more likely to occur in this compact system than in the Earth to Mars case. If this is true, then life might spread more easily between planets that huddle close together around their star. This would increase the chances of life taking root in such neighborhoods of space. Some theories go beyond this. They imagine rocky or icy fragments wandering between star systems in the Milky Way galaxy, carrying with them the seeds of life. According to one mathematical analysis, planetary systems might even capture some of these travelers. If so, life could hop not just from planet to planet, but from star to star. Yet there is a problem. The passengers inside those rocks, tiny living organisms, would have to endure journeys lasting millions or even billions of years. Surviving the endless cold and deadly radiation of interstellar space for such unimaginable spans of time seems almost impossible. So far, no one has found direct proof that lithopanspermia has ever happened, neither within our solar system nor between stars. But imagine if one day scientists discover living creatures on both Earth and Mars that clearly share the same biological fingerprint. That would be powerful evidence that life really can leap across the void from one world to another. Until such a discovery is made, the idea remains a fascinating but unproven possibility. A possibility that keeps inspiring experiments, debates, and bold new research. Of course, lithopanspermia itself is not a simple idea. For life to survive such a journey, a whole chain of very specific events would need to occur. An asteroid impact strong enough to eject rocks, organisms surviving inside those rocks, and then a safe landing. Many scientists argue that bacteria would almost certainly perish in the hostile vacuum of space, blasted by radiation and frozen by the cold. And yet, in the early days of our solar system, colossal asteroid strikes were common, and even today impacts still occur, especially within the asteroid belt. A far more daring theory, known as directed panspermia, was introduced in the early 1970s. It was introduced by Francis Crick, one of the Nobel Prize-winning scientists who helped discover the structure of DNA. Along with his colleague Leslie Orgel, they suggested something extraordinary, that life on Earth did not simply appear here on its own. It was deliberately placed here by an advanced alien civilization. At the time, many scientists doubted that life could have reached Earth naturally, reached it through either radiation-driven panspermia or lithopanspermia. And so Crick and Orgel asked, what if intelligent beings from the stars sent life here on purpose? Orgel himself was more cautious about the idea than Crick, and both men admitted there was no hard proof. Still, they speculated on what kind of evidence might one day support their claim. Not everyone treated the matter so seriously. The astrophysicist Thomas Gold proposed a tongue-in-cheek version of the idea. He suggested that life on Earth might have started from alien cosmic garbage, leftover waste accidentally dumped by extraterrestrial visitors. While amusing, Crick and Orgel grounded their own argument in a more thoughtful concept, a concept called cosmic reversibility. Their reasoning was simple. If human civilization might one day develop the ability to send life to another planet, then perhaps another civilization had already done the same. A civilization far older and more advanced had done the same thing to Earth long ago. As a hint in support of their theory, Crick and Orgel pointed out something striking. The genetic code, the molecular language of DNA, is the same for all living things on Earth. They speculated that if life was deliberately seeded here, the first microorganisms might even have contained a hidden message. A message inside their DNA, planted by the alien senders almost 4 billion years ago. But after so many ages of mutation and natural evolution, any such message would likely have been erased, leaving no trace behind for us to read today. Back in the 1970s, both abiogenesis and panspermia were considered plausible. Abiogenesis is the idea that life began naturally on Earth. Panspermia is the idea that life came from space. No experiments could clearly favor one over the other, but modern science has since gathered stronger evidence for abiogenesis, while panspermia, especially in its directed form, remains mostly speculation with little to support it. There is, however, another possibility that scientists take more seriously, called pseudopanspermia. This theory suggests that while full living organisms may not have traveled here from space, the raw ingredients for life almost certainly did. Molecules, such as amino acids, sugars, and the building blocks of DNA, are known to form in space, and many of them have been found inside meteorites, comets, and even grains of cosmic dust. Over time, these molecules could have rained down on the young Earth, mixing and combining until life itself eventually emerged. One of the most famous stories of supposed extraterrestrial life came in the mid-19th century. On the 14th of May in the year 1864, a meteorite broke apart in the skies above the French town of Orgeau. It scattered about 20 fragments across the countryside. A century later, in 1965, scientists examined one of these fragments. It had been carefully preserved in a sealed glass jar since the day it fell. To their astonishment, they discovered what looked like a seed capsule hidden inside the meteorite. While the stone's glassy outer shell appeared untouched, it seemed at first like undeniable evidence. Evidence that life had truly fallen from the stars. But closer study revealed a clever fraud. The seed was nothing more than that of a common European rush plant. It was glued neatly into the rock, with coal dust used as camouflage. The supposed fusion crust of the meteorite was actually just hardened glue. The trickster behind the hoax was never identified, but many historians suspect they were trying to sway the heated 19th century debate. A debate over whether life could arise spontaneously from non-living matter. In the year 2000, 17 astronomers stumbled upon a discovery that left the world both amazed and puzzled. While scanning the skies with the powerful Pan-STARRS telescope in Hawaii, they noticed a peculiar visitor drifting silently through space. This strange object shone with a reddish tint and stretched to an astonishing size. Nearly the length of 4 football fields, about 400 meters long. What made it truly extraordinary was not just its size or color, but its path through the heavens. Unlike the countless comets and asteroids that belong to our own solar system, this wanderer followed an unusual orbit, an orbit that revealed something astonishing. It had come from far beyond, from the deep unknown between the stars. For the very first time in human history, we had detected an interstellar object, a traveler from another star system passing through our cosmic neighborhood. Among the scientists who studied it was Avi Loeb, a Harvard professor known for bold and unconventional ideas. He proposed that this mysterious visitor might not be a simple rock at all, but possibly an artifact, something crafted by an alien civilization. He even suggested that it could be connected to the concept of directed panspermia, the idea that advanced beings might deliberately send out vessels carrying the seeds of life to distant worlds. Yet, despite the daring and exciting nature of this theory, most experts remained cautious. They argued that the object, while strange, could still be explained by natural processes, perhaps a fragment from a shattered planet or an oddly shaped comet wandering between the stars. Still, the mystery remains, and the discovery has sparked one of the most fascinating debates in modern astronomy. Was this interstellar visitor a mere cosmic rock, or could it have been a messenger from another civilization? For many years after its discovery, scientists puzzled over the mysterious object called Oumuamua. They tried again and again to understand what exactly it was. At first, astronomers could not decide whether it was an asteroid, a comet, or something entirely new. Over time, most of them leaned toward calling it a comet. Yet there was a problem. Oumuamua did not behave like any comet ever seen before. Normally, comets release gas and dust when they get close to the sun. This creates a bright tail that pushes them slightly off course. Oumuamua, however, moved in a way that was much stranger and harder to explain. The leading idea is that it may be covered with a thin layer of frozen hydrogen. When sunlight touches this hydrogen, it heats up and turns into gas, escaping into space. That gentle but steady push not only speeds up Oumuamua, but also shifts its path as it drifts through our solar system. Another piece of evidence that supports this theory is its reddish color. This strange hue hints that the object has been bombarded for countless ages by cosmic rays, high-energy particles that travel across the galaxy. Such bombardment could have lasted for millions or even billions of years. Over this vast time, these rays may have helped Oumuamua gather its coating of frozen hydrogen, a coating which now makes it move in such an unusual way. Even so, scientists are not completely sure. The mystery remains unsolved, and that is why many of them have been dreaming of a daring mission, a mission to chase this cosmic traveler. Their idea is bold: send a spacecraft fast enough to catch up with Oumuamua, even though it is already far away from Earth. This effort has been given a name: Project Lyra. Project Lyra would use a clever trick known as a gravity assist. the spacecraft would first launch from Earth loop around our planet once, and then head toward Jupiter. When it reached the giant planet, Jupiter's enormous gravity would pull it in and then fling it outward at tremendous speed. This slingshot effect would send the probe racing back toward Earth for a second flyby, where it would gain even more speed before shooting off into deep space toward Oumuamua. If all went as planned, this probe would become the fastest spacecraft humanity has ever built. But Oumuamua is not the only interstellar visitor that has caught our attention. Project Lyra is also interested in another mysterious traveler, a comet named Borisov. Unlike Oumuamua, which was first spotted by professional astronomers in 2017, Borisov was discovered in August of 2019. It was discovered by an amateur stargazer named Gennady Borisov. Scientists quickly realized that, like Oumuamua, Borisov had come from outside our solar system. This made it only the second confirmed interstellar object ever seen. Borisov is fascinating in its own right. Its cloud of gas and dust is astonishingly smooth. It is without the usual lumps, cracks, or rough features that are common in comets from our solar system. When astronomers studied the light reflecting off Borisov, they were stunned. It appeared far cleaner than any comet ever observed. This means that Borisov is made of more pristine material, possibly unchanged since the earliest days of its birth star system. Even more surprising was the sheer amount of material it shed. Borisov released over 400 pounds of dust every single second. On top of that, it contained an unusually large amount of carbon monoxide, far more than comets from our neighborhood normally carry. What made this stranger still was that the levels of carbon monoxide were not evenly spread across the comet. This hinted that Borisov may have formed close to its original star before being nudged outward by the pull of giant planets. Another clue to its uniqueness came from the way Borisov reflected sunlight. Its light was far more polarized than that of any other comet, a property never seen before. Combined with its unusually smooth cloud, this suggests that Borisov had never passed near a star, not even its own. That would make it one of the purest and most untouched cosmic objects ever studied. With two such strange visitors appearing in only a few years, astronomers have grown eager to investigate more. They hope that by chasing and studying interstellar travelers like Oumuamua and Borisov, they can discover how comets form and how they journey through the galaxy, and perhaps even how solar systems, including our own, first came to be. Project Lyra itself began on the 30th of October in the year 2017. It was launched by the Initiative for Interstellar Studies, often shortened to I4IS. At first, most scientists thought that Oumuamua was simply moving too fast for any spacecraft to ever catch it. But in January of 2022, new research suggested something astonishing. If carefully planned, a probe launched from Earth could reach Oumuamua in about 26 years. This would make a direct study possible. Originally, I4 is proposed launching a mission as early as 2021. They were hoping to reach Oumuamua within just 5 to 10 years. The plan involved a daring maneuver. After passing Jupiter to pick up speed, the spacecraft would dive extremely close to the Sun, within only 3 to 10 times the Sun's radius. There, it would use the Oberth effect to give the probe an incredible push, a powerful burst of acceleration gained by firing engines deep in a strong gravitational field. Later studies, however, suggested other opportunities. New mission windows in the years 2030 and 2033 could work as well. These versions included an extra trick called the V-infinity leveraging maneuver. It would fine-tune the spacecraft's speed and direction before the big boost near the Sun. The estimated travel time was about 22 years. So even though the very first chance had been missed, humanity still had ways to try again. As planning continued, scientists also looked at less dangerous options. Instead of sending a spacecraft so close to the Sun, another strategy relied on a Jupiter-Oberth maneuver. It would use Jupiter's gravity for the final push. This would open launch windows between the years 2026 and 2033, depending on the route chosen. Researchers also considered futuristic technologies, solar sails that use sunlight for propulsion, giant laser sails pushed by beams of light from Earth, and even nuclear-powered spacecraft. These advanced methods could one day help us chase down fast interstellar objects more easily. The greatest challenge, however, is not only catching up with Oumuamua, but also slowing down enough to study it properly. If a spacecraft simply speeds by, it will only have a few short moments to take pictures and collect data. But if it can slow down, it might orbit or even land, unlocking secrets that could never be learned from afar. Despite all the obstacles, scientists remain hopeful. Astronomers like Gregory Laughlin and Darrell Seligman believe that while the challenges are huge, the rewards are equally great. They carefully studied the possibility of such missions. A mission to an interstellar visitor could change our understanding of the universe forever. One early plan suggested launching a small probe weighing only a few dozen kilograms aboard a Falcon Heavy-class rocket. Protected by a heat shield similar to that of the Parker Solar Probe, it would have used a Jupiter flyby and a sundive. It would have done this to gain the speed needed to catch Oumuamua. If it had launched in 2021, it could have worked. Later studies, however, pointed to new chances in the early decades ahead. Launch windows in the years 2030 or 2033 could still allow a spacecraft to use a solar Oberth maneuver, this time at a safer distance of 6 times the Sun's radius. Such a journey would take more than 20 years. While that may sound like a lifetime, it is worth remembering that the Voyager probes are still sending back data today. They launched more than 45 years ago. In more recent years, a group of researchers has been developing new and exciting mission ideas. They are working under the Project Lyra team at the Initiative for Interstellar Studies. One of their proposals points to a possible spacecraft launch in the year 2028. Unlike earlier suggestions that relied on the extremely difficult solar maneuver, this plan would use a Jupiter-Oberth maneuver. A spacecraft dives dangerously close to the Sun for a massive speed boost in the solar maneuver. In this method, the spacecraft would swing around the giant planet Jupiter to gain a powerful slingshot effect. While still complex, this option is far more realistic with the technology humanity currently has at its disposal. But the scientists are not stopping there. Beyond the traditional rockets that have carried every mission so far, they are daring to explore new propulsion methods that sound almost like science fiction. Among these are spacecraft that could be pushed by sunlight itself or powered by beams of laser light. This is a method called solar and laser electric propulsion. Some are even considering laser-driven sails inspired by the bold Breakthrough Starshot project. This project imagines sending tiny probes across the vastness of interstellar space. On an even more ambitious level, there is nuclear propulsion, which could provide enormous power for journeys far beyond our solar system. Each of these futuristic technologies could completely transform space exploration. It could allow spacecraft to chase down mysterious objects like Oumuamua in a fraction of the time it would take with ordinary rockets. Although the very first hopes of reaching Oumuamua in the early years of the 2020s were never realized, scientists have not abandoned the dream. They know there will be many more opportunities to launch in the decades to come. And with every passing year, propulsion technology continues to advance. The dream of sending a human-made spacecraft to explore Oumuamua remains alive and vibrant. Or perhaps another strange interstellar traveler that drifts into our cosmic neighborhood Around the world, researchers are determined to find the best path forward, keeping the hope of such a historic mission burning brightly. The very first thing that startled astronomers about this strange visitor from the stars was that the numbers simply refused to make sense. And that was unusual, deeply unusual, because in astronomy, numbers are not just digits on a page, they are the sacred language of truth. When a star brightens or dims, when a comet flares or an asteroid spins, astronomers trust the numbers to guide them. Numbers reveal the hidden dance of gravity, the pull of light, and the structure of matter itself. Normally, scientists can take their observations, feed them into equations, and predict with remarkable precision how an object will behave. They can say where it will be tomorrow, how fast it is moving, and why it shines the way it does. But in the year 2017, when a bizarre object named Oumuamua swept through our solar system, the numbers told a story that felt impossible, almost like a riddle written by the universe itself. To understand the puzzle, it helps to know how familiar cosmic visitors behave. Asteroids and comets, the small wanderers of our solar system, usually change in brightness as they spin. It is a simple play of sunlight. When a broadside faces Earth, it reflects more light and appears brighter. When a narrower side turns our way, the reflection weakens and the object looks dimmer. This brightening and dimming is normal and expected. For most asteroids and comets, the shift is modest, perhaps 20% or 30% brighter or darker, never anything too dramatic. But Oumuamua, the interstellar stranger, refused to follow this ordinary script. Roughly every 8¼ hours, its brightness swung wildly. At moments it dimmed so much that it nearly vanished from sight, slipping close to invisibility. Then, without warning, it brightened again, glowing nearly 10 times stronger than its faintest appearance, only to fade once more with uncanny regularity. The changes were sharp, mechanical, almost as though some hidden clock were ticking inside it. This was not the gentle flickering of a lumpy asteroid shaped like a potato. It was not the irregular blinking of a comet with fragments tumbling off. It was something entirely alien to what astronomers had seen before. Its light curve, that strange pattern of brightening and fading plotted over time, was unlike anything known in planetary science. It pointed to an object stretched out into a bizarre form, a shape that seemed to defy the natural rules of physics. Dr. Karen Meach of the University of Hawaii, who led the international team of astronomers, later described the shock of those early days. When we first saw the light curve, she recalled, many of us thought the data must be wrong. Objects simply don't form with aspect ratios that extreme. And indeed, the cautious calculations revealed something astonishing. Oumuamua appeared to be at least 6 times longer than it was wide. Some interpretations stretched that number to 10 times longer than wide. To put it more simply, it was not shaped like a boulder or a chunk of rock. It was more like an enormous cosmic needle drifting through space. Imagine, if you will, a football field, the grand expanse of green grass 100 yards long. Now shrink its width until it is only 10 yards across. That more or less was the kind of proportions the numbers suggested for Oumuamua. No known natural process in planetary science could explain such an extreme shape. How could such a long, thin body form naturally? And even if it somehow did, how could it survive the brutal violence of interstellar travel, the constant bombardment of dust, the crashing of micrometeorites, and the shattering forces of time? But the strange shape was only the beginning. Its spin made the mystery deeper. Most asteroids and comets behave like tops spinning smoothly around their shortest axis. Over millions upon millions of years, countless collisions and gravitational nudges tend to push them into this stable form of rotation. It is like a coin that eventually settles flat after wobbling. But Oumuamua was not obeying this cosmic tendency toward order. It was tumbling chaotically in what astronomers call non-principal axis rotation. To human eyes, if one could stand close enough to watch, it might have looked like a baton spinning and flipping unpredictably. It was performing cosmic gymnastics in the blackness of space. Such tumbling raised unsettling questions. Had a recent collision knocked it into this unstable spin? Or was its internal structure so strange, so unlike anything we had ever seen, that it simply did not rotate like ordinary rocks? Could it be hollow inside or filled with layers of materials with unusual densities? Or, in the most provocative whisper of possibility, had it been designed this way, built for some purpose beyond our understanding? The surface only deepened the riddle. Spectroscopic studies which split the light reflected from an object into its component colors showed that Oumuamua was wrapped in a dark reddish coat. This hue is often seen on distant objects in the solar system, and it's usually the sign of organic compounds that have been cooked and scarred by cosmic rays over enormous spans of time. This suggested something astonishing. Oumuamua was ancient, so ancient it might have been older than the solar system itself. It had traveled the deep darkness between stars for millions, perhaps billions of years. It traveled before slipping almost by accident through our small neighborhood of planets. Yet, despite this unfathomable age, its surface showed no obvious scars. Where were the pockmarks of micrometeorites? Where was the erosion that cosmic radiation should have inflicted? It was as though time itself had left it largely untouched. And then came its behavior near the sun, the moment when the strangeness deepened into something utterly baffling. A comet, when warmed by the sun's heat, usually begins to shed material. Ice boils into gas dust, is released, and together they form the glowing halo called a coma, and the trailing stream we know as a comet's tail. It is this brilliant outgassing that has lit up the night skies for millennia, inspiring awe and fear in every civilization that has watched them. But Oumuamua was different. As it swung past the sun, warming to temperatures that should have boiled away any ice, it stayed completely silent. No gas, no dust, no coma, no tail, nothing. It was as if it had shrugged off the sun's warmth, refusing to reveal its secrets. But the final shock, the one that truly left scientists stunned, was its acceleration. Careful tracking revealed that as Oumuamua moved away from the sun, it was not simply coasting on gravity's leash. It was speeding up just slightly, but undeniably. The acceleration was tiny, only about 1/4 of a millimeter per second squared. But in the careful, precise world of astronomy, even such a small deviation matters. For a comet, this would be explained easily. Jets of gas burst from its surface as ice sublimates, providing a push like invisible thrusters. But here there were no jets, no gas, no dust, nothing that could account for the mysterious force nudging it along. Dr. Marco Micheli of the European Space Agency, who led the orbital analysis, described the situation with haunting simplicity. We are seeing an acceleration that requires a force, but we cannot see the mechanism. It is like watching a car speed up without being able to find its engine. Theoretical explanations soon multiplied. Perhaps Oumuamua was venting gases so faint and so finely spread that our instruments could not detect them. Perhaps it was made of exotic materials that absorbed sunlight in unusual ways, heating up and re-emitting energy to give it a subtle push. One bold hypothesis suggested it might be a hydrogen iceberg, a massive chunk of frozen hydrogen formed in the cold clouds between stars. As it warmed, the hydrogen could sublimate, invisibly propelling it forward. But even that idea raised enormous difficulties. How could such a fragile structure survive a journey of millions of years through space without evaporating entirely? And then came the bolder ideas that stirred both fascination and discomfort. Could Oumuamua be an artificial object? Could it be a light sail, a thin, broad structure designed by an intelligent civilization to ride on the gentle pressure of starlight? The acceleration matched what one might expect from such a device. The extreme elongated shape could even be understood as a way to maximize surface area for such propulsion. Was it possible that what we were seeing was not a rock at all, but technology from the stars? Dr. Avi Loeb of Harvard University became the most outspoken champion of this possibility. He argued passionately that science should not dismiss ideas simply because they felt uncomfortable. When we encounter something truly new, he said, we must be willing to consider all explanations, even those that challenge our assumptions about the universe. His words rang both bold and unsettling. If Oumuamua truly were artificial, it would mean we had just witnessed evidence of intelligent life beyond Earth. This debate revealed a deeper division in the scientific community. On one side stood those who insisted on exhausting every possible natural explanation before even whispering the extraordinary. On the other side stood those who felt that ignoring the extraordinary possibility was itself unscientific. The truth was, no one had an answer that fit cleanly. The natural explanations required unusual materials, invisible forces, or fine-tuned scenarios never before observed. The artificial explanations seemed too bold, too daring for many to accept, and yet the questions refused to go away. As Oumuamua faded beyond the reach of telescopes slipping into the constellation Pegasus, it left behind only mysteries. How could such an extreme shape hold together? What invisible hand had accelerated it? And perhaps most haunting of all, how many more like it were, gliding silently through our solar system, unnoticed, because we simply were not looking at the right moment. For the first time in human history, we had witnessed an object born around another star, a true interstellar visitor, and it refused to play by the rules. It was too long, too thin, too unpredictable, too strange. Researchers ran countless computer simulations trying to recreate its birth. They imagined it forming near massive stars, shattering in crowded clusters, or being carved by exotic chemical processes. None of the models matched the data perfectly. The most honest words came from Robert Werrick, the astronomer who had first spotted it through the Pan-STARRS telescope. "We've learned more from this one object than decades of theory ever taught us," he admitted. "But what we've mostly learned is how much we don't know." And so Oumuamua spun away at nearly 40 kilometers per second, tumbling like a lost messenger from another world. It carried with it not answers, but questions. Questions that stretched the limits of science, philosophy, and perhaps even our sense of what it means to be alone in the cosmos. The cosmic cigar, as many nicknamed it, had tumbled into our skies and then back into the dark. Leaving us humbled, it did not explain itself. It only reminded us that the universe is not simple, not ordinary, and not entirely understood. It left behind the whisper of a possibility both thrilling and terrifying, that our solar system is not as typical as we once thought, and that out there in the deep darkness, other messengers are still traveling, carrying secrets stranger than our imagination can yet reach. The reaction of the scientific community to the sudden and mysterious appearance of Oumuamua was unlike anything astronomy had seen before. Scientists all around the world immediately sensed that something truly unusual had entered their field of vision. Whether they were working in great observatories in universities or in small research groups, at first it might have seemed like just another faint dot of light sliding across the dark canvas of the night sky, no different from the countless asteroids or comets already catalogued. But within hours, and certainly within days, it became clear that this was not a familiar kind of traveler. This was not one more icy fragment left over from the birth of our solar system, nor was it a wandering rock on a predictable loop around our sun. This was something altogether different, an interstellar visitor, the very first one humanity had ever confirmed. And what made the discovery even more astonishing was that it had already passed by us, slipping into our neighborhood of space and then vanishing again almost before we had truly recognized what it was. That fleeting encounter shook astronomy to its core. For generations, astronomers had dreamed of detecting such an object, but most believed it was only a remote possibility, the kind of event that might occur once in a century. Yet suddenly in the year 2017 it had happened. The consequences rippled outward almost immediately. Within only a few months after Oumuamua's departure, astronomy quietly began to transform. It was as though a switch had been flipped in the minds of scientists. The way we scanned the heavens, the way we interpreted what we saw, and even the fundamental questions we asked began to shift. The search for interstellar objects, once dismissed as little more than a thought experiment, abruptly became a top priority. What followed was a whirlwind of urgency. Emergency meetings were called at observatories and research centers across the planet. Normally, astronomy is a slow and careful science. Proposals for new projects take years to pass through layers of committees, debates, and budgetary reviews. Money flows like a cautious trickle, and every decision is weighed with extreme care. But after Oumuamua, the mood changed dramatically. Funding committees that had once rolled their eyes at interstellar research now opened their wallets. Projects worth many millions of dollars were suddenly approved with breathtaking speed. The message was clear and undeniable. Humanity had been caught unprepared when its first confirmed visitor from another star system appeared, and such a mistake must never be repeated. The immediate reaction was to retool the way we scan the skies. Telescopes and surveys originally built for other purposes were suddenly adapted for the new task. In the state of Arizona, the Catalina Sky Survey reprogrammed its systems almost overnight. It had long been devoted to detecting asteroids that might pose a danger to Earth. No longer would it look only for objects circling our own sun. Now it would search for the strange mathematical signatures of hyperbolic orbits, the peculiar flight paths that mark the journey of something not bound to our solar system at all. These hyperbolic curves were the fingerprints of true wanderers from interstellar space. Other programs quickly followed. In New Mexico, the Lincoln Near-Earth Asteroid Research Project upgraded its equipment. NASA's telescope known as NEOWISE was also adjusted to increase its chances of catching a fleeting traveler from beyond. It had already been watching the skies in the infrared, yet perhaps the most ambitious preparation of all was taking shape far to the south in the deserts of Chile. There, construction crews were already working on the Vera C. Rubin Observatory, an enormous facility that promised to be one of the most powerful tools ever created for astronomy. Its original mission had been sweeping and grand to map the structure of the universe itself, cataloguing galaxies by the billions and tracing the shifting dance of stars across the heavens. But in the wake of Oumuamua, its mission expanded. The Rubin Observatory would also become the ultimate hunter of interstellar visitors. When completed, it would scan the entire sky visible from its mountaintop home every few nights. It would produce data so vast it could only be measured in mountains of digital storage. Artificial intelligence systems would sift through this deluge of information, trained carefully to recognize the faintest hints of motion that belonged not to local asteroids, but to alien wanderers. Buried in all that data they hoped would be the next Oumuamua, Dr. Mario Jurich, an astronomer from the University of Washington, captured the magnitude of the task with a vivid metaphor. He directed much of the Rubin Observatory's data operations. Searching for interstellar visitors, he explained, was like hunting for needles in a haystack. But in this case, the haystack was the size of the observable universe. His words carried both awe and determination. Oumuamua had already shown that such needles did exist. The challenge now was to be ready to catch them before they slipped away again. The urgency was reinforced by simple arithmetic. If Oumuamua was not a once-in-an-epoch fluke, but a representative of a larger population, then dozens of similar objects should be passing through. Perhaps even hundreds should be passing through our solar system every year. Many would be far too tiny, or too faint for our instruments to detect. But a significant number should still be within reach of the new generation of telescopes. This realization overturned the old assumptions completely. For decades, astronomers had believed that spotting such an interstellar object would be extraordinarily rare, perhaps only once every 10 years or even less often. That assumption was now revealed to have been wrong by orders of magnitude. The space between stars, once pictured as a vast and lonely emptiness, suddenly seemed far more crowded, and the reaction was not confined to the United States. A wave of international cooperation followed. The European Space Agency pressed forward with plans for a successor to its famous Gaia mission, a spacecraft designed to measure the positions and motions of stars with exquisite precision. By tracking stars so carefully, astronomers hoped to trace back the flight paths of interstellar objects. They hoped to identify not only where they had come from, but also perhaps the exact stellar system that had cast them out. NASA's Planetary Defense Coordination Office broadened its scope to include these strange new visitors. It had previously focused only on protecting Earth from dangerous asteroids. Even amateur astronomers scattered across the globe with their modest backyard telescopes were recruited into the effort. Their observations fed into worldwide networks thanks to clever software that allowed even small contributions to become valuable. Yet the task was not an easy one. Interstellar objects behave differently from anything born within our solar system. They do not loop endlessly around our sun like comets or asteroids. They sweep in along hyperbolic trajectories, their speed carrying them through our neighborhood in only a matter of months. The window of opportunity is tiny, sometimes no more than a few weeks. The time between the moment an object becomes bright enough to detect and the moment it fades forever into the dark. To meet this challenge, new artificial intelligence programs were trained to recognize unusual motions in real time. The goal was breathtaking. Within hours of discovery, telescopes around the world could be redirected. They could capture every detail before the visitor disappeared again into the Black Sea between the stars. This feverish preparation grew out of the lessons of Oumuamua itself. The object had remained visible for only about 11 weeks, scarcely enough time to measure its shape, its brightness, and its strange acceleration. Scientists were left with far more questions than answers. What was it made of? Why did it brighten in such an unusual way? What mysterious force had launched it into interstellar space? The mysteries lingered unsolved, leaving astronomers with a deep sense of frustration. Next time, they vowed, things would be different. Plans were drawn up for rapid response missions. Instruments would stand ready to analyze the chemistry of any new arrival within hours of discovery. Radar systems would map its contours in detail. Ambitious space agencies even considered sending spacecraft to intercept interstellar travelers directly. The Japanese Aerospace Exploration Agency studied the use of solar sails. These are vast sheets of reflective material that could propel spacecraft with the pressure of sunlight, potentially allowing them to chase down such fast-moving visitors. At NASA's Jet Propulsion Laboratory, engineers brainstormed whether existing spacecraft could be redirected to meet one of these messengers from afar. The hunt also broadened beyond the visible spectrum. Radio astronomers developed techniques to detect faint emissions of gas that ordinary optical telescopes might miss. Infrared instruments were tuned to catch the heat signatures of objects too dark to reflect much sunlight. Some even speculated that sensitive instruments designed to detect gravitational waves might one day be used to sense the passage of massive interstellar bodies, ripples in space-time from colliding black holes. The possibilities seemed endless, and with those possibilities came profound implications. If interstellar objects were common, then they might represent a natural system for transporting matter between star systems. Imagine a fragment of a world encased in protective rock or ice, carrying within it complex organic molecules or perhaps even primitive microbes, surviving a long journey across the galaxy. Suddenly, the ancient hypothesis of panspermia felt far more plausible. The idea that life could spread from one world to another, riding on drifting celestial debris. Astrobiologists began preparing protocols to analyze any future visitor with meticulous care. They designed sterile methods for collecting samples. They dreamed up spacecraft capable of capturing fragments without contamination, and they planned Earth-based spectroscopy programs to search for the chemical fingerprints of organic life. Even the search for extraterrestrial intelligence was reshaped by Oumuamua. It had long focused on listening for radio signals. Some researchers wondered aloud whether advanced civilizations might send physical messengers rather than fragile beams of light across the void. Perhaps interstellar space was dotted with artificial probes, silent carriers of information coded into their structures or trajectories. In response, new scanning protocols were adopted. Every time an interstellar object was discovered, radio telescopes listened carefully for patterns. Optical instruments searched for metallic surfaces or geometric shapes that might hint at artificial design. None were found, but the very act of looking marked a new frontier in the search for company among the stars. The transformation of astronomy was swift and profound. What had once been a purely theoretical curiosity became an urgent and practical science. Entire careers shifted in the space of months. Scientists who had spent decades running computer models of imaginary interstellar objects suddenly found themselves analyzing real ones. New journals appeared, conferences overflowed, and the excitement was palpable. It felt as though a new branch of science had been born overnight. Every night, automated telescopes swept the skies. Algorithms worked tirelessly, searching for the unusual motions that might reveal another wanderer. The atmosphere among astronomers was no longer a question of if, but of when. Somewhere in the silent expanse beyond the planets, the next messenger was already on its way. And beneath all the technical urgency lay something deeper, something almost spiritual. Humanity had for the very first time encountered a confirmed fragment of another star system. We were no longer simply onlookers gazing passively at the cosmos. We had become participants in a larger story, part of a galactic web in which worlds occasionally share their fragments with one another. Each visitor was a kind of gift, a sample of another place delivered across unimaginable distances to our doorstep. A new era had begun, the era of interstellar archaeology. Each future visitor would carry within it a story written in the language of minerals, ice, and gas. Each fragment would be a piece of a foreign planet, perhaps ripped loose by a cosmic collision or flung outward by the gravity of its home star. By studying these fragments, humanity would slowly piece together a grand mosaic of how planets form, and how they evolve, and perhaps even how life spreads among the stars. The telescopes stood ready, the algorithms waited, and in the dark, beyond the reach of our sight, another wanderer was already making its way toward us. On the very first day of July in the year 2025, the mighty Atlas telescope was carrying out its familiar nightly duty. It was standing proudly on the dry and windswept plateau of Rio Hurtado in Chile. Every night, as darkness wrapped itself around the mountains, this great machine lifted its electronic eyes toward the heavens. Its job was both humble and heroic, to sweep across the endless southern skies, searching patiently for small wandering pieces of rock and ice, silent travelers that might one day cross Earth's path and bring danger. Hour after hour, the telescope traced invisible lines across the starry dome. It recorded the faintest flickers of light, comparing patterns and searching for anything unusual among the countless celestial fires. But on this particular night, something different appeared. It was not a grand flash or a spectacular explosion, but a tiny, shy glimmer, a glimmer that seemed almost lost against the deep backdrop of Sagittarius, that crowded region of the Milky Way where stars shine thick and bright. The automated detection system raised a signal. It had been trained like a keen guard dog to notice the smallest disturbance. A faint dot hardly brighter than the background noise of the sky had betrayed itself. Most dots like this turned out to be nothing, just errors, cosmic rays, or ordinary asteroids. Yet this one moved, and its motion told a strange story. It was sliding across the sky with a speed that was far too quick, and more importantly, in a direction that no normal member of our solar family should have taken. The stars held their places fixed in their ancient harmony. But this little point of light was slipping out of step as if it belonged to another music entirely. At exactly 3 hours and 47 minutes past midnight local Chilean time, the alert reached Dr. Larry Deno. Dr. Deno was the principal investigator of the Atlas project, working from the University of Hawaii. For many years, he and his team had spent their lives watching the heavens for asteroids that could one day threaten Earth. They had grown sharp-eyed, not only with their instruments, but also with their instincts. An experienced astronomer could often feel almost in the bones whether a new object belonged to the Sun's household or came from elsewhere. This new arrival, given the temporary tag C 2025N1, instantly triggered that instinct. The whispers in the data said one clear thing: this was no child of our solar system. The pace of events quickened. Within only 6 hours of its first sighting, careful orbital calculations had been completed. What the numbers revealed shook even the most cautious scientists. The object's orbital eccentricity stood near the staggering value of 6. Eccentricity is a measure of how stretched or circular an object's path is. For astronomers, this was like seeing a red flare in the sky. Orbits of planets and comets bound to the Sun are stretched ellipses always less than 1 in eccentricity. Exactly 1 would mean a perfect escape parabola, but 3 Atlas had an eccentricity around 6 far greater than 1. That single number told astronomers everything they needed to know. This object did not belong here. It was not captured. It was not native. It was a visitor sweeping in from the endless dark between the stars, paying us only a brief call before it slipped away again forever. Its speed confirmed it about 61 kilometers every second. It was faster than any asteroid, faster than any comet ever observed inside the solar system. It was faster even than Oumuamua or Borisov, the 2 earlier visitors from the stars. This was the swiftest interstellar traveler humanity had ever caught sight of. What made the discovery even more electrifying was not just what it was, but when it had been found. Back in the year 2017, the world had been stunned by the sudden appearance of Oumuamua, the first interstellar object ever seen. Yet Oumuamua had been spotted only after it had already passed the Sun and was speeding away. This gave astronomers just a few short weeks to scramble for data before it vanished forever. Many questions had been left unanswered, and debates about its true nature raged for years afterward. This time, however, fortune smiled. The new object, C 2025N1, later nicknamed 3I, Atlas, had been detected on its way in. It was still approaching the heart of our solar system. That meant astronomers had months, not weeks, to watch it, measure it, and peel away its secrets. They could do this before it swung past the Sun and returned to the silent ocean of interstellar space. The naming of the object followed a careful and time-honored code. The letter C marked it as a comet even before its physical features were fully understood. The year 2025 stamped the time of its discovery. The letter N told astronomers it was the first such object discovered in the second half of July. and the atlas paid tribute to the telescope survey that had caught it. Later, once official review had been completed, the International Astronomical Union would add it to the growing list of interstellar travelers. It would be the third confirmed member following Oumuamua, which carried the title 1I, and the comet Borisov called 2I. But in truth, even before its name was formalized, 3I, Atlas, had already begun to show that it was no ordinary discovery. At a distance of about 4.5 astronomical units from the Sun, it was already alive with activity. This is around the orbit of mighty Jupiter. Astronomers detected a delicate but certain halo of gas and dust surrounding its nucleus. This misty envelope, known as a coma, stretched nearly 25,000 kilometers outward, a glowing cloud born from ices and volatile compounds, escaping into space as sunlight touched the surface. Unlike Oumuamua, which had remained a quiet star-like point without visible activity, this object was unmistakably a comet, a living, breathing body shedding its icy skin as it warmed. The Gemini North Telescope in Hawaii soon delivered the first detailed images. The pictures showed a small fuzzy ball with a stubby tail pointing away from the Sun, exactly the kind of profile people expected from a comet. This sight alone thrilled theorists, for many had long predicted that interstellar visitors should resemble comets more than asteroids. And now here was confirmation shining in front of them. News spread at lightning speed. Within 2 days of the public announcement, 3I, Atlas had become the most intensely studied comet in human history. The European Southern Observatory's Very Large Telescope in Chile began breaking apart the light from the comet. It broke it into its component colors, teasing out the chemical recipe hidden in its glow. The Hubble Space Telescope, circling high above Earth, was swiftly reprogrammed to aim its keen eyes at the comet. It took images sharper than any ground-based telescope could provide. Across the globe, giant radio dishes swiveled to listen for even the faintest whisper that might suggest artificial origin. Though most astronomers expected silence, they still listened just in case. The contrast with the frantic days of 2017 could not have been clearer. Back then, Oumuamua's sudden arrival had thrown the community into chaos. Observation time had been begged for at the last minute. Communication had been rushed, and many opportunities had slipped away. Now, after years of preparation, the world was ready. Protocols had been drafted, observation slots reserved, and international channels of cooperation strengthened. When 3I, Atlas, appeared, humanity did not stumble. Instead, it stood ready, united, and eager. Dr. Robert Werrick, the astronomer who had first laid eyes on Oumuamua 8 years earlier, could not help but feel a quiet sense of pride. "We learned from our first visitor," he remarked with a satisfied smile. "This time we had plans ready, we had instruments waiting, and instead of scrambling to catch up, we were already leading the way." His words carried the weight of experience. Humanity had been caught unprepared before, but not this time. The first detailed spectroscopic readings painted a fascinating picture of the newcomer. Its surface was coated with silicate minerals and laced with complex organic molecules, materials that bore a resemblance to the comets formed in the frozen outer reaches of our own solar system, and yet there were whispers of something foreign in its chemistry. The isotope ratios, those delicate fingerprints of cosmic origin, did not match what we were used to seeing. They hinted at a birthplace around a star unlike our own Sun, in a planetary system that had followed a different path of birth, death, and renewal. This was no ordinary comet. It was a messenger carrying with it the memory of skies that had never shone upon Earth. When astronomers measured its spin, they found that it rotated once every 29 hours, a slow and steady rhythm compared to Oumuamua's frantic 8-hour tumble through space. The way its light brightened and dimmed suggested a body that was either nearly round or only gently stretched out. Not the bizarre cigar-shaped enigma that had caused endless debates about Oumuamua's true nature. For the first time, scientists were looking at what they had always expected an interstellar comet to resemble, but nature, with its love for surprises, refused to make things so simple. As the comet drew closer to the Sun, it began to reveal unexpected behavior. Instead of releasing gas in a smooth and predictable pattern, the comet erupted in sudden, irregular bursts. As sunlight warmed its icy crust, it was as if hidden pockets of frozen material lay buried within its nucleus, releasing their contents only when exposed to sunlight at odd angles. Some scientists suspected that its spin might be more complex than it appeared, bringing different regions into the sun's glare in unexpected ways. Spectral lines, signatures of particular chemicals, flickered in and out, appearing one moment and fading the next. Its glowing tail showed faint but curious asymmetries. This suggested that its interior structure was far stranger than any ordinary comet born within our solar system. The implications of this discovery were staggering. Finding a single interstellar visitor like Oumuamua had shocked the scientific world. Finding a second, Borisov made some wonder whether chance had played a role. But now, within the short span of only 8 years, humanity had encountered a third. The message could not be ignored. Statistical models now suggested that such wanderers must pass through the inner solar system far more often than anyone had dared to imagine, perhaps several times in every single decade, and they came from all across the sky. Oumuamua had entered from the direction of Vega in the constellation Lyra. Borisov had arrived from a different path. Now, 3I. Atlas came streaking in from Sagittarius, nearly 90 degrees away on the celestial sphere. The heavens were sending a clear message. Interstellar space was not empty. It was alive with debris, the fragments of shattered worlds drifting endlessly between the stars. Even its speed deepened the mystery. Moving at 61 kilometers per second relative to the Sun 3I, Atlas traveled far faster than could be explained by the ordinary ejection of a comet. Such a tremendous velocity suggested something extraordinary, perhaps a violent birth in the chaos of a giant planet's gravity, or the furious blast of a dying star ejecting material into space. Or maybe its journey had begun in a distant corner of the galaxy, with gravity accelerating it during a voyage that had lasted millions, even billions of years. Computer simulations were set, running at once, trying to rewind its path through the galaxy and trace its origin. But the task was almost impossible. Over such immense spans of time, the comet would have drifted past countless stars, each tugging at it with the faint pull of gravity nudging its path in subtle ways. Still, the earliest results hinted that it might have come from the thick disk of our galaxy, perhaps born in a planetary system that had been torn apart when its parent star met a violent end. The reaction of the public and the media was very different from what it had been 8 years earlier. When Oumuamua had appeared, headlines had been filled with wild speculation about aliens and artificial origins. This time the story was one of awe and scientific wonder. Newspapers and broadcasts celebrated the chance to study a pristine sample of another star system, a sample delivered to us freely across the void. Astronomers emphasized natural explanations, careful not to repeat the frenzy of speculation. And yet, beneath the caution, there was a shared sense of reverence, as if everyone knew that something truly rare and precious had arrived. For these encounters were not random gifts of chance. Each interstellar traveler was a cosmic time capsule, carrying within its dust and ice the story of a world we might never set foot upon. 3I. Atlas bore in its chemistry the history of another star's creation, its elemental composition, and the furnace of nuclear reactions. Reactions that had burned long before our own sun was born. Its isotopes whispered secrets of a distant dawn. Week by week, as it approached the sun, its glow grew brighter, its presence more undeniable. The second messenger from the stars was speaking not with words but with the universal languages of light and chemistry. And this time, humanity, wiser from its first encounter, was truly prepared to listen. The path of 3I. Atlas was far more than a mere curved line scratched across the starry canvas of the night sky. It was not just a trace left by a wandering stone against the backdrop of constellations. It was instead a story, a vast and unbroken tale. A tale written not with ink or paper, but with mathematics, with gravity, with the silent forces that rule the heavens. This tale had been unfolding for millions upon millions of years, stretching across distances so great that the human mind can hardly imagine them. It had wandered through countless light years of interstellar space, slipping between the stars, passing unseen across the hidden gulfs between suns. To understand where this strange visitor was heading, astronomers first had to ask a much harder question. Where had it been? This was not a simple puzzle. It was more like a detective story, though not the kind one might read in novels. Novels of stolen jewels, clever suspects, and dimly lit crime scenes. Instead, this was a detective story of the cosmos. The suspect here was a lonely traveler, a wanderer without a home, carrying within it tiny hints and quiet clues from the farthest edges of the galaxy. For scientists who are used to studying planets, asteroids, and comets, the case of 3I, Atlas, was unlike anything familiar. The orbits of the worlds that circle our sun are usually neat, predictable ovals, ellipses, as mathematics calls them, forever bound to the gravitational embrace of the sun. Comets too, though they may stretch their paths into long loops, eventually circle back, returning again and again after years or centuries. But 3I, Atlas, did not behave like these loyal companions of the solar family. Its course was of a very different kind. The orbit of this traveler was hyperbolic, not elliptical. In the mathematics of space flight and astronomy, the eccentricity of an orbit holds the key, the number that tells whether it is a circle, an oval, or something else. For anything bound to the sun, the eccentricity must be less than 1. Exactly 1 would mean a perfect escape parabola. But 3I, Atlas, had an eccentricity around 6, far greater than 1. That single number told astronomers everything they needed to know. This object did not belong here. It was not captured. It was not native. It was a visitor sweeping in from the endless dark between the stars, paying us only a brief call before it slipped away again forever. This alien traveler was destined to brush closest to our star on the 30th day of October in the year 2025. On that day, it would swing to within about 1¼ astronomical units of the Sun. An astronomical unit is the average distance between the Earth and the Sun, and 1¼ of that is roughly the same distance as the orbit of Mars. This distance was something of a cosmic gift. It was near enough that telescopes could study the object in sharp detail, but not so close that the ferocious heat of the sun would strip it completely bare, boiling away any ice or fragile compounds locked inside it. A little earlier than that closest solar pass, the traveler would also come nearest to our own world, at about 1 2/3 astronomical units, still much farther than Earth's orbit and far too distant to pose any kind of danger. Humanity was safe, but deeply curious. Yet what fascinated astronomers, even more than its safe distance, was its direction of arrival. 3I, Atlas did not come gliding in along the familiar flat plane of the planets, the disk on which Mercury, Venus, Earth, Mars, and the others circle the Sun. Instead, it came slashing in almost sideways, entering from the constellation Sagittarius at a steep angle nearly perpendicular to the planetary plane. This unusual side entry made astronomers pause. Most known interstellar visitors approached in gentler, more aligned paths, but this angle suggested a more tangled story. a deeper history buried in the structure of the Milky Way itself. To try to read that story, scientists turned to their most powerful tools, computer simulations. With these, they began to rewind time, to play back the orbit of 3I, Atlas in reverse, as though a cosmic film were being rolled backward. The movie stretched not for hours or days, but for millions of years, each moment carrying the traveler farther from our neighborhood. The challenge, however, was staggering. Every nearby star, every massive object within a few hundred light-years of the Sun had at some point tugged on this wanderer, tugged on it with its own gravity. Each tug was a fingerprint, but together they blurred and smeared the record, warping the once clear line of its past. To trace its true beginning was almost impossible, even with the fastest supercomputers humanity had yet built. Even so, the most likely explanation began to take shape. 3I. Atlas seemed to have been born in the galactic thin disk, the broad region of the Milky Way where stars like our own Sun are most common. Perhaps once upon a time it had circled peacefully around a star, one of many small icy bodies orbiting a distant sun. But something had happened. Perhaps a giant planet the size of Jupiter or larger had given it a slingshot kick, flinging it into the deep. Or perhaps its star had reached the end of its life, blasting out fierce stellar winds, or collapsing in a mighty explosion, tearing loose its smaller companions and casting them into the night. Whatever the case, 3I, Atlas, had been unmoored, sent to drift and condemned to wander. One scientist leading this enormous effort of reconstruction explained the difficulty with a metaphor that caught the imagination. Dr. A.C.F. F of the University of Hertfordshire. It is like trying to investigate a cosmic murder, he said. But this crime scene is millions of years old, stretched across hundreds of light years, and every star we examine could be the suspect. Worse still, the evidence itself has been bent and twisted by gravity's pull, changing shape again and again over time. The speed of the object gave another set of clues. 3I. Atlas was rushing through the solar system at about 61 kilometers every single second relative to the Sun. Such a breathtaking velocity could not arise from chance alone. It demanded a history either of a violent ejection during some catastrophic stellar event, or of a slower, patient acceleration gathered through countless encounters with other stars over vast stretches of time. One possibility was that it had been born from an explosion hurled outward by the death of a star, or flung in a near collision with a black hole or neutron star. The other possibility was quieter but just as remarkable, that over millions of years it had been nudged again and again, each small tug adding speed, until at last it was racing along at this tremendous pace. When astronomers compared 3I, Atlas, to its interstellar predecessors, its individuality shone through. The first of these strange visitors, discovered in 2017, had been called Oumuamua. It had entered our solar system from the direction of Vega, the bright star in the constellation Lyra. The second, known as Borisov, had come from Cassiopeia. And now 3I, Atlas, had arrived from Sagittarius, in an entirely different quarter of the sky. The three arrivals, each from a separate direction about 60 to 90 degrees apart, told scientists something profound. There was no single cosmic highway feeding interstellar wanderers into our solar system. They came from everywhere, from every angle, as if the galaxy itself were filled with drifting debris. That realization was stunning. It meant that our solar system was not some lonely outpost in an empty void. It was part of a vast river system of cosmic material. Dust pebbles, rocks, and shattered fragments of long-lost stars and planets flowed constantly between systems, weaving an unseen network of exchange. Every interstellar visitor was a messenger from this traffic, a silent letter from another place and another time. The larger galactic picture made the story even richer still. Our solar system is not fixed in place. It races around the heart of the Milky Way at about 220 kilometers each second, completing one full circuit of the galaxy only once every 225 million years. During its million-year journey 3I, Atlas, would have crossed the paths of many dozens of stars, each encounter bending its line slightly, each encounter shaping the long script of its destiny. Its chemical fingerprint added still more depth. Studies of its light showed that its surface contained silicate minerals like the sand and rock of Earth, and complex organic molecules. Yet the precise ratios of certain isotopes were not like those of our solar system. The tiny variations in atomic composition, they whispered of a different birthplace of a chemistry forged around another star, one with its own unique history. Perhaps it was born around a star older than the Sun, one that had fewer heavy elements. Or perhaps it formed in a younger system, one enriched by the ashes of many stellar deaths. Even more intriguingly, the steepness of its entry suggested that it had traveled for much of its time through the galactic thick disk, a population of stars older than those of the thin disk. This meant that 3I, Atlas, might contain materials forged in an ancient chapter of the Milky Way's story, carrying within it the echoes of times long past. The future of the object, however, was already certain. The mathematics of orbital mechanics left little room for surprise. After its close brush with the Sun in late October of 2025 3I, Atlas would accelerate outward once more, retracing its hyperbolic path. By the early months of the year 2026, it would pass beyond the outer planets, heading off toward the constellation Perseus. Unlike the messy, uncertain path of its arrival, its departure could be mapped with confidence for thousands of years. It would carry with it subtle scars from its brief encounter with our system, tiny chemical alterations, faint structural shifts from solar radiation and heat. Perhaps one day in a distant future, if it drifted into another planetary system, alien astronomers would find it. They might read those faint scars and realize that this traveler had once bathed in the light of our yellow sun. This certainty of prediction gave humanity an extraordinary chance. Unlike with Oumuamua, which had been discovered only after it was already leaving, we now had months of warning. Observatories could prepare, could coordinate their telescopes to capture every detail. Space agencies even debated the possibility of a daring robotic probe, a spacecraft that might be launched swiftly to chase and meet the traveler while it lingered still within our cosmic neighborhood. Such a mission, though difficult, was no longer unthinkable. And so, as 3I, Atlas continued its slow approach. Its orbit was not just a curve on paper. It was a timeline stretched across deep history. This object had been wandering through interstellar space for longer than human beings had walked the Earth upright. When it had first been cast out from its parent star, our own ancestors were still little more than clever apes, roaming the grasslands of Africa. Since then, millions of years had passed, and those apes had given rise to us. Creatures who had built cities, crafted telescopes, and invented mathematics precise enough to read the tale of this visitor, 3I, Atlas, was more than a curiosity. It was a reminder that the Milky Way is not a still life, not a frozen portrait of unchanging stars. It is alive, it is dynamic. Material is forever moving from one place to another. Stars are born, they live and they die. Planets form and are destroyed. Worlds fling fragments into the dark, and those fragments drift, carrying stories, carrying memories, carrying the ancient signatures of their birthplaces. By studying such wanderers, we can peer into the past of distant systems, glimpsing not only where they were born, but also when. Every observation of 3I, Atlas, was like another sentence in this long cosmic narrative. Its journey had begun millions of years ago, around a star that might already have died, and it would continue long after our own sun had exhausted its fuel and faded away. For one brief interval in this immense span of time, it would glow in our skies, lit by the rays of our star, and then it would vanish again into silence, slipping back into the unmeasured reaches of interstellar space. In its silent passage lay the truth that we too are part of this great story, a species fortunate enough to witness, however briefly, the visit of a messenger from the depths of time and from the farthest corners of the galaxy. Understanding the true size of 3I, Atlas, is not at all an easy task. When scientists study asteroids or comets that wander within our own solar system, they have the advantage of sending spacecraft close. A robotic probe can sweep past such an object, take direct photographs, and measure its shape and size with precision. That is how we know, for example, what the surface of comets like Halley or Tempel 1 look like. But with an interstellar traveler like 3I, Atlas, things are much more difficult. This mysterious visitor did not come from the family of objects that circle our sun. Instead, it arrived from the wide, dark reaches between the stars, and it never comes close enough for us to send a spacecraft to inspect it directly. Because of this distance and its fleeting passage, astronomers must rely on clever and indirect methods to guess its size. The main tool they use is something called photometry, which is simply the careful study of light. In this case, astronomers measure how much sunlight the object reflects as it drifts across the night sky. The brighter it looks through their telescopes, the more sunlight it is bouncing back toward Earth. But the brightness by itself is not enough to give a size. An object can appear bright either because it is very large or because it has a shiny surface. On the other hand, something dark and dull can appear faint, even if it is quite large. To deal with this problem, scientists use a concept called albedo, which is just a measure of how reflective the surface is. A fresh surface covered in bright ice has a high albedo and would suggest a smaller body. It would need less surface area to reflect the observed amount of sunlight. A surface darkened by dust, soot, or carbon-rich material has a low albedo. This would mean the object must be larger to reflect the same amount of light. By combining the observed brightness with different possible values for the albedo, astronomers can place limits on the size of 3I, Atlas. The first studies provided hints that this was no tiny pebble from the stars. Though small compared to planets, it was clearly bigger than many asteroids, and certainly larger than some of the only other interstellar visitors that humanity has ever been lucky enough to detect. These early measurements suggested that its diameter is somewhere between 60 meters and 120 meters. If its surface is as dark as many long-period comets that swing around our sun, its size is likely closer to the larger end. Coated with carbon-rich dust that absorbs much of the sunlight. If, however, its surface includes bright patches of fresh ice shining like tiny mirrors in space, then its diameter could be closer to the smaller figure. To understand what this means, it helps to compare 3I, Atlas, with the other rare travelers that came before it. The first confirmed interstellar object, discovered in 2017, was called Oumuamua. That strange wanderer was about 100 meters long, though it was difficult to measure exactly. Because it did not have a neat, round shape, instead it appeared elongated like a cigar, or perhaps flattened like a pancake, which made size estimates uncertain. The second interstellar visitor was Comet Borisov, discovered in 2019. Borisov was far larger than Oumuamua, with a core more than 1 full kilometer across. This made it much easier to detect and to study. 3I. Atlas rests between these two. Not as massive as Borisov, yet more comet-like than Oumuamua, placing it in a curious middle ground. In many ways, its size is similar to the icy wanderers that belong to our own solar system, suggesting that comets from distant stars may not be so very different from those that orbit our Sun. But size is not the only puzzle. Astronomers also noticed that the brightness of 3I, Atlas, did not remain steady. Instead, it flickered and changed in a repeating pattern. This meant that the object is not a perfectly round ball. It could be stretched out, lumpy, or oddly shaped, perhaps a broken fragment of a larger body. As it spins in space, different sides catch the sunlight and reflect it toward Earth. This creates bright and dim periods like a slowly turning lantern. The record of these flickers, which scientists call a light curve, can reveal clues about the shape and rotation, but it also complicates the effort to measure its true size. The amount of light reflected changes depending on which part of the surface is turned toward us. The fact that we detected 3I, Atlas, at all is a wonder in itself. Interstellar visitors are extremely difficult to see because most of them are very small, even at its brightest 3I. Atlas was faint, requiring medium or large telescopes to detect. It was visible for only a short window of time as it passed through the crowded starfields of the Milky Way. Had it been only half its actual size, astronomers believe it would have escaped detection entirely, slipping unnoticed back into the eternal dark between the stars. Its small size also has consequences for its physical strength. Smaller cosmic bodies are usually fragile, especially when they pass near stars. The gravity and heat can pull them apart, breaking them into pieces. In our solar system, countless comets that skim close to the Sun are torn into fragments and vanish in bright flashes, so-called sun grazers. But 3I, Atlas, seemed sturdy enough to endure its approach. Observers did see faint signs of gas, escaping tiny jets of vapor released as surface ice turned into gas. This is normal cometary behavior and does not necessarily mean the object was falling apart. In fact, its survival suggested that it is tougher than many small comets of our own system. Understanding the size of 3I, Atlas is also important for what it tells us about the unseen population of interstellar objects. If this one is typical, then our galaxy may be swarming with billions of similar icy fragments drifting silently among the stars. They would be the cast-off debris of planet formation, flung away from their birthplaces during the violent early years when planets and moons were colliding and migrating. The fact that we have now seen 3 such objects, Oumuamua Borisov and 3I, Atlas, in just a few short years suggests that the true population is enormous. With new wide-field telescopes and sky surveys beginning soon, astronomers expect to discover many more. Each new find will help refine the picture of how large or small these objects usually are and how common they might be. But the small size of 3I, Atlas, also leads to deeper mysteries. Was this object once part of a far larger body, perhaps a fragment broken away from a planet or a dwarf planet that was shattered by cosmic violence? Or did it form as a solitary icy lump and then get ejected into the emptiness between stars? The irregular brightness and stretched shape seem to support the first possibility that it is a shard from a bigger world. Computer simulations of planetary systems show that collisions and gravitational slingshots can easily fling such fragments into interstellar space. Once set adrift, they wander endlessly, carrying with them the scars of their origin. Whatever its story 3I, Atlas has given us a rare and valuable gift. Even though it is small, it offers us a window into the hidden realm of interstellar debris. Each one of these fragments links the violent births of planets to the greater story of the cosmos. Every interstellar visitor is a messenger from another system, bearing silent testimony to the forces that shape worlds. When scientists examine 3I, Atlas, one of their first questions is whether it behaves more like a comet or more like an asteroid. This is not merely a matter of naming. It reveals what the object is made of and how much ice it contains. Comets, when warmed by a star, release gases as the ice on their surfaces vaporizes. This usually creates a glowing cloud called a coma, and often a long, sweeping tail that stretches across space. Asteroids, by contrast, are mostly dry and rocky. They reflect sunlight, but they do not release gas or dust. 3I Atlas, however, fits neatly into neither category. Instead, it seems to blur the line between the two, showing qualities of both. This is part of what makes it so fascinating. It suggests that interstellar objects may evolve into strange hybrids during their journeys across unimaginable distances and times. When astronomers first spotted 3I Atlas, they noticed faint hints of activity. Careful studies of its brightness revealed a thin, hazy glow around the core. This was the sign of a coma, created as some of its ices began to melt while approaching the sun. Yet this coma was weak and subtle. It was more than the silence of Oumuamua, which had no visible coma at all. But it was far less dramatic than Borisov, whose brilliant tail stretched tens of thousands of kilometers. In this way, 3I Atlas occupies a middle ground, active enough to reveal that it carries ice, but quiet enough to suggest that part of its surface is sealed under a crust that resists melting. Instead of a sweeping tail, it displayed only a thin halo of dust. This faint activity tells us part of its story. One idea is that 3I Atlas has been traveling through interstellar space for millions upon millions of years. During that time, it would have been struck endlessly by cosmic rays and micrometeorites, each impact and particle slowly changing its surface. Over ages, this bombardment could create a tough, dark shell, sealing the interior ice beneath a hardened crust. When warmed by the sun, this shell would trap much of the ice inside, allowing only faint traces of gas and dust to escape. Another idea is that 3I Atlas was never very rich in ice from the beginning. Perhaps it formed closer to its parent star in a warmer region where ices were scarce. In that case, it would be more rocky in nature, with only modest amounts of frozen material hidden within. Whatever the truth, the faint coma of 3I Atlas adds to its strange identity. Part comet, part asteroid, neither fully one nor the other. It is a reminder that the universe rarely offers us neat categories. Instead, it presents us with hybrids, fragments, and mysteries that challenge our understanding. Astronomers were not only interested in the shape and motion of 3I Atlas, they also carefully studied the dust and gases it released as it drifted near the sun. This is one of the best ways to understand what such a traveler is made of and how it behaves under the warmth of a star. When scientists compared 3I Atlas with Borisov, the second interstellar visitor, they saw a striking difference. Borisov threw out hundreds of kilograms of dust every single second, producing a dazzling spectacle in space. Its outflow was so powerful that its tail stretched long and bright, easy to spot even with small telescopes. 3I Atlas, however, was much quieter. At its most active moment, it only released a handful of kilograms per second, far weaker than Borisov. This explained why it never grew a magnificent tail that backyard astronomers could admire. Yet even though its outpouring was faint, it was still meaningful. That little stream of dust and gas carried secrets about its birthplace and its long journey. By analyzing the thin, ghostly glow around it, its coma astronomers detected water vapor, carbon monoxide, and possibly carbon dioxide. These substances are the very same frozen ices that exist in the faraway frozen zones of planetary systems. Among them, the high level of carbon monoxide was especially fascinating. It hinted that 3I Atlas must have been born in a place of extreme cold, maybe even farther from its parent star than the Kuiper belt lies from our own sun. This supported the theory that such interstellar objects are thrown outward from the icy rims of young planetary systems, pushed away by the gravitational force of giant planets. The fact that 3I, Atlas, lacked a long and shining tail was not just an observation about appearances, it also revealed something about what was happening beneath its surface. The heat of the sun likely did not reach deep inside. Instead, it warmed only the shallow outer layers of its cracked and battered body. From there, gas escaped slowly and quietly instead of erupting in violent blasts. Over countless ages, its surface had been altered by harsh radiation and by the impacts of countless microscopic collisions. These processes probably built a hardened crust over its outer skin which acted like a lid. It kept the deeper ices trapped within. This led astronomers to ask a larger and more intriguing question. Do all interstellar visitors age and change in the same way? Or does each follow its own unique journey of transformation? Borisov, for example, stayed icy and very active, giving off clouds of gas like a classic comet. Oumuamua, in contrast, displayed no visible activity at all. It remained silent and mysterious. 3I. Atlas landed somewhere between these two extremes, producing only a faint ghost-like halo. Could it be that some interstellar wanderers grow protective shells that keep their inner ices hidden, while others remain bare and exposed? These differences are not just curious details. They are essential clues that help scientists piece together how the endless emptiness of interstellar space reshapes icy bodies, reshapes them over spans of millions upon millions of years. Each traveler is like a record, carrying in its behavior and its structure the story of its survival across vast cosmic distances, and there is an even deeper meaning hidden in all this. The faint coma of 3I. Atlas touches on one of the most daring ideas in science, the possibility of panspermia. This is the thought that the raw ingredients of life, or even the microscopic seeds of life itself, might travel from star to star, travel on icy wanderers like comets. If a body such as 3I, Atlas can still hold on to carbon-rich compounds and frozen water after drifting for eons through deep space, it could act as a messenger. Drifting through deadly radiation and freezing cold, it could carry the chemistry of life between distant worlds. Even the weak outgassing we saw proves that these compounds can survive and be released again. Released when the traveler draws close to a warm star. When we place Oumuamua Borisov and 3I, Atlas side by side, a clearer picture begins to emerge. Each of these visitors is strikingly different, almost as if they are characters in a cosmic storybook. Oumuamua was silent, with no visible activity, and its strange motion made it one of the greatest mysteries in modern astronomy. Borisov, by contrast, behaved like a familiar friend, showing off its comet-like nature in spectacular form. 3I. Atlas rests in the middle ground, neither silent nor loud, but softly whispering with its faint release of dust and gas. Together, they show us that interstellar objects are not identical. They're as diverse and unpredictable as the worlds where they were born. When astronomers first realized that such visitors were entering our solar system, they began to think of them not just as icy rocks, but as travelers, each carrying its own personality. Oumuamua, the first, was like a riddle wrapped in silence. It had no bright tail, no outgassing, yet it seemed to move as though guided by some invisible hand. Some scientists guessed it might be coated with metallic hydrogen. Others suggested an ancient crust of dark, hardened organics. Whatever the truth, it kept its mysteries locked away. Then came Borisov, the second interstellar wanderer. Unlike Oumuamua, Borisov behaved exactly as astronomers would expect. It released gas and dust, freely produced a bright coma, and grew a long, glowing tail. It was textbook in every sense, as if it had leapt straight from the pages of a comet manual. and then arrived 3I, Atlas, the third visitor. It sits in the middle ground between the two extremes. Like a comet, it contains ice, but part of its surface is hidden under an ancient shell. It is active, but not explosive. It releases matter into space, but it does so in a restrained and quiet manner. This middle path makes it especially fascinating because it shows that interstellar travelers are not a single category. They are a diverse family of wanderers, shaped by where they were born, shaped by the billions of years they have spent drifting through the galaxy and by the harsh trials of the vacuum. One of the most vital details astronomers have studied about 3I, Atlas, is its spin. At first, this might seem like a small matter, but it is actually a window into how it behaves. The way an object spins decides how sunlight warms its surface. This, in turn, affects how gas and dust are released. If it tumbles chaotically, sunlight will fall unevenly, sometimes uncovering hidden icy spots that suddenly flare up. If it spins smoothly and evenly, then the heating is spread out. This produces a gentler, steadier release. To uncover its spin, scientists use light curves, the repeating patterns of brightness that appear as it turns, just like a lumpy potato that reflects more light on one side than the other. 3I, Atlas flickered slightly as it rotated. The changes were faint but clear enough to confirm that it was spinning. Early results suggested that 3I, Atlas, takes between 9 and 12 hours to complete a full turn. This is quite normal since many comets in our own solar system rotate in just a few hours, or as long as nearly a full day. This moderate pace is important. It means the object is strong enough to endure its lonely journey through space without breaking apart, but not spinning so quickly that it tears itself into pieces. Yet the flickers in its light also carried another secret. They were not smooth and regular, but uneven. This hinted that 3I, Atlas, is oddly shaped, stretched, or lopsided. It may also not be spinning around a single steady axis, but instead wobbling in a clumsy tumble. Astronomers call this non-principal axis rotation, but in simpler terms it means an unstable, irregular spin. Such tumbling is not rare. Small objects often end up in such a state after countless nudges from stars, planets, or even tiny collisions. For an interstellar traveler like 3I, Atlas, it makes perfect sense. Over millions of years drifting through the galaxy, it would have been pulled and pushed by many forces. It would also have been struck by tiny grains of matter. Each little disturbance would slowly change its spin until it became unsteady. This could also explain why its gas and dust release looks uneven. Sunlight would strike different surfaces at unexpected times. If 3I, Atlas is indeed tumbling, that tells us something very important about its structure. A fragile body would probably crack apart under such stress, but 3I, Atlas remains whole. This suggests that its interior is stronger and tougher than it looks. Perhaps a tightly packed blend of dust and ice. Its spin also preserves a record of its past. Every close pass near a star can change the way a comet-like object spins, as bursts of gas escaping from the surface act like small rocket engines. Over time, these little pushes could speed it up, slow it down, or send it wobbling in new directions. The moderate rotation of 3I, Atlas hints at two possibilities. Either it has not had many such encounters during its vast journey, or its hardened shell has kept most of its activity controlled, preventing dramatic changes. When astronomers looked at the strange visitor called 3I, Atlas, one of the first things they wondered about was its spin. It seemed to turn in space in a way that was not entirely steady, not completely calm, yet not wildly tumbling either. This led some scientists to suggest that the reason for this odd motion might go back all the way to its dramatic first moment, the moment when it was first thrown out of its home star system. In the early ages of any solar system, long before the planets settle into the quiet orbits we see today, things are far from peaceful. Giant planets many times larger than Jupiter often wander about in unstable paths. Their immense gravity acts like a cosmic slingshot. It hurls smaller bodies, icy comets, rocky asteroids, and frozen fragments outward with incredible force. It is entirely possible that 3I, Atlas, was caught in such an ancient act of planetary violence. If so, the way it spins today may be nothing less than a fossil, a preserved clue of that ancient catastrophe. A physical memory written in the movement of its body as it drifts endlessly between the stars. When astronomers compared this visitor to the two interstellar objects that had come before, they began to notice a fascinating pattern. The first interstellar wanderer ever seen by humanity was named Oumuamua. It behaved in a way that was both puzzling and exciting. It tumbled in a chaotic and unpredictable fashion, spinning end over end like a poorly thrown baton. Its body was long and stretched more like a giant cigar, or perhaps a thin shard. This gave it an almost alien appearance. The second interstellar traveler, called Borisov, was far more familiar. It rotated smoothly and calmly, behaving very much like the comets of our own solar system. It shed gas and dust in a way that felt almost comforting to astronomers who had spent their lives studying such things. 3I, Atlas did not copy either of its predecessors exactly. It seemed to occupy a space in between. Its spin was moderate, not completely steady, but not entirely wild either. This balance suggested something important, that interstellar visitors are not one single kind of object, but rather a diverse family of travelers. Each one carries its own story, a history written in the way it spins, the way it shines, and the way it reacts to the sunlight. But motion and spin are only one part of the story. Astronomers have another tool, perhaps even more powerful, for peering into the secrets of these wandering messengers. That tool is spectroscopy, the careful study of light. Every element and every molecule in the universe leaves its own fingerprint when it absorbs or reflects light. If you shine sunlight on an object and then spread that light into a rainbow, you will see tiny dark lines or dips where specific colors are missing. Using a prism or a spectrograph, those missing colors are the signature of particular atoms or molecules. In this way, light itself becomes a messenger, carrying with it the secrets of chemistry. For interstellar objects, these fingerprints of light are especially valuable. They tell us what the object is made of, what elements and molecules are frozen or buried within it, and by extension they hint at the nature of the star system where it was born. When astronomers turned their spectrographs toward 3I, Atlas, they expected strangeness, something utterly foreign. But what they found astonished them for a different reason. It looked remarkably familiar. Despite the fact that it had come from another star system, the pattern of light reflected from its surface bore a strong resemblance. A resemblance to the comets of our own solar system. Its chemistry was not exotic, not entirely alien, but strikingly similar to the frozen bodies that orbit our sun. This discovery carried with it a profound implication. The rules that shape comets may not be unique to our solar system. They may be universal, operating in much the same way in star systems scattered across the Milky Way galaxy. If comets form in our solar system by gathering ices, rocks, and gases in the cold outskirts, then perhaps comets are forming in that same fashion around countless other stars, far from the sun. Among the chemical signals observed, the strongest one came from water ice. In the near-infrared part of the spectrum, astronomers detected subtle dips that reveal the unmistakable presence of frozen water. This was no surprise, for water is one of the most abundant and important substances in the cosmos. It exists on planets, moons, comets, and in icy clouds floating freely between the stars. Its presence in 3I, Atlas, told us that this object had been born in a cold and distant part of its parent star system, far from the warmth of its star where ices could survive without melting away. In other words, It came from a place like the Kuiper Belt or Oort cloud of our own system, those distant icy reservoirs beyond Neptune and Pluto. But water was only the beginning. 3I. Atlas also released gases like carbon monoxide and carbon dioxide. These are familiar to us, for comets in our solar system shed the same gases as they approached the Sun. Yet the exact mixture of these gases was not quite the same as we usually see. 3I. Atlas showed a higher proportion of carbon monoxide compared to water than most of our local comets. This unusual ratio hinted at something about its place of origin. Perhaps it had formed even farther from its star than the comets of our Kuiper Belt, in regions so cold that carbon monoxide could freeze solid. Or perhaps its parent star was dimmer and cooler than our Sun, forcing its icy worlds to form at greater distances than ours. In either case, its chemistry painted a picture of an origin story slightly different from the one we know, a story shaped by colder environments and longer distances. Then came one of the most exciting discoveries of all. When scientists looked deeper into the spectrum, they found hints of complex molecules. These were not simple ices like water or carbon dioxide. They were more complicated organic compounds and hydrocarbon. Molecules built from carbon and hydrogen, the same building blocks that form the backbone of life on Earth. These tiny signals showed up as faint absorption bands in both the ultraviolet and near-infrared regions of the spectrum. Their presence suggested that during its unimaginably long journey through interstellar space, cosmic rays and high-energy particles had been bombarding its surface. Over time, this steady radiation transformed some of the simple ices into more complex organic matter. This process is well known in our own solar system. Long-period comets, those that travel for millions of years in the distant Oort cloud, also show similar transformations. Even the frozen surfaces of distant moons like Triton and Pluto are darkened and reddened by the same process, their surfaces scarred by the slow work of cosmic radiation. In this way, 3I, Atlas, was not unusual. It had undergone the same kind of space weathering as countless other icy bodies, only on a grander and longer scale. The discovery of these organic molecules thrilled astronomers. It hinted at something much larger than just one comet. If objects like 3I, Atlas, carry organics, then the chemistry of life might not be confined to Earth or even to our solar system. As it shed gas and dust into space, 3I, Atlas was scattering not only water and carbon monoxide, but also complex carbon-based molecules. These molecules are the seeds of chemistry potential ingredients for biology. Over billions of years, as interstellar wanderers travel from one star system to another, they may deliver such seeds to young planets, planets just forming their oceans and atmospheres. It is not hard to picture a scenario where a planet receives a sprinkling of organic compounds from a passing comet like 3I, Atlas, a planet still covered in molten seas and barren continents. Those molecules might then take part in the slow chemistry that eventually gives rise to life. In this way, interstellar objects become cosmic couriers, delivering the raw beginnings of biology from one corner of the galaxy to another. Life, or at least the ingredients for life, may not be born in isolation. It may be shared, carried and spread by countless icy wanderers over countless billions of years. The data told astronomers other things as well. Not all interstellar visitors are alike in how they preserve their ancient material. Borisov, for instance, looked almost as if it had been frozen in time since the day of its birth. A pristine comet that had not been altered by radiation or time. 3I, Atlas, by contrast, told a more layered story. Its outer surface looked dark, weathered and scarred by billions of years of exposure to cosmic rays. Yet when astronomers looked beneath that aged crust, they found evidence of fresh, untouched ice hidden below, ice that had not been altered since the earliest days of its formation. This structure, with an old rugged surface covering younger, purer material within, was exactly what astronomers would expect. Expected if the object had truly been wandering through interstellar space for eons. It bore the marks of its long journey on the outside, but preserved within it the heart of its ancient beginnings. There was another intriguing clue as well. In the glowing gas cloud surrounding 3I, Atlas astronomers detected silicate dust. It was revealed as bright spikes in the infrared part of the spectrum. Silicates are rocky materials, usually born in warmer regions, closer to a star, not in the icy outskirts. Their presence suggested that 3I, Atlas, was not a simple ball of ice, but a mixture of rock and ice together. This hinted that it may have formed in an intermediate region of its home system, somewhere between the hot, rocky inner planets and the frozen belt of distant comets. In the chaotic early days, strong gravitational forces could have easily stirred and jumbled materials from different regions together. This would create icy bodies laced with rock before casting them outward into space. 3I. Atlas, then, was a mixture, a hybrid of worlds. It carried within it both the cold chemistry of the outer system and the rocky grains of the inner system. Perhaps the most surprising discovery of all, however, was also the most ordinary. Apart from its slightly unusual mix of gases and the weathering caused by cosmic radiation 3I, Atlas did not seem to contain anything exotic. It was in many ways an ordinary comet. This ordinariness carried an extraordinary message. It meant that the same chemistry that shaped our own comets was not unique. The same kinds of ingredients, the water, the carbon dioxide, the organics, the silicates, are likely being assembled in countless star systems, all across the Milky Way. The building blocks of planets, oceans, and perhaps even life itself are not locked away in our own solar system. They are scattered generously across the galaxy, waiting to be gathered by other stars and other worlds. 3 wanderers had crossed the enormous silent gulf between the stars and had entered our solar system. They were not just pieces of ice and rock drifting aimlessly through the void. They were visitors, each one a messenger from the deep, unlit regions of interstellar space. Each carried a story written in its very substance and in the way it moved. To astronomers, these 3 visitors were like rare books carried across the ocean from distant, unknown lands. Every time one appeared, it was as though the universe had handed them another chapter in an ongoing saga, a galactic story slowly revealed piece by piece. Each arrival raised new questions, each departure left mysteries unsolved, and the contrast between them was so sharp that they startled even the most experienced scientists. The first of these wanderers, the one that shocked the world and made history, was discovered in 2017. It was named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. And indeed it was the very first object ever confirmed to have come from another star. When astronomers realized what they were looking at, they were stunned. Here, finally, was proof that fragments from other solar systems could and did make the long and dangerous journey across space. Yet the behavior of Oumuamua was unlike anything ever seen. It gave no signs of being a comet. There was no faint mist, no glowing gases escaping from its surface, no shimmering tail unfurling behind it. Instead, it slipped silently past, dark and mysterious, like a lonely stone flung across a cosmic ocean. Its silence was unsettling, its strangeness unforgettable. For generations, comets had been defined by their fiery breath when warmed by the sun. Yet this object, although it passed well within range of solar heat, refused to reveal even a wisp of activity. It was mute, enigmatic, and impossible to fit neatly into the categories of asteroid or comet. It was as if the universe had sent us a puzzle without a solution. 2 years later, in 2019, another visitor appeared, and this one brought a completely different kind of story. This second traveler was named 2I, Borisov, after the amateur astronomer Gennady Borisov, who first spotted it. Unlike Oumuamua, this object behaved much more like the comets that astronomers were familiar with. When sunlight touched it, it began to breathe out gases and dust. It formed a long, shining tail that stretched behind it like a streamer. Through telescopes, it looked almost like the comets that had dazzled human eyes for centuries. And yet, even this second visitor was not ordinary. Careful spectroscopic studies revealed that Borisov carried with it vast amounts of carbon monoxide, 10 to 50 times more than had ever been seen in comets native to our own solar system. This was no trivial difference. Such an unusual abundance suggested that Borisov had been born in a place far colder and stranger than anything near our sun. Its home star system must have had regions so frigid that exotic ices unstable in our neighborhood could remain frozen. In that sense, Borisov was like a bottle of foreign wine. Its taste revealed the soil, the climate, and the history of the distant land where it had been made. By studying it, astronomers were not only learning about a comet, but also about the environment of a planetary system countless light years away. And then not long afterward, in 2025, the universe gifted humanity with yet another traveler. This one was called 3I, Atlas. If Oumuamua was the silent messenger and Borisov the textbook comet with a strange accent, Atlas was something else entirely. Long before it came anywhere near the inner planets, Atlas began to show dramatic activity. While it was still beyond the orbit of mighty Jupiter and far from the sun's warming rays, even at that great distance, it released streams of gas and dust into space, building around itself a vast glowing cloud called a coma. The coma swelled to astonishing proportions, expanding until it was roughly 50,000 kilometers across, so large that it could be compared to the size of Mercury, the smallest of the planets. This was breathtaking. It was as if Atlas had decided to announce itself loudly before it even reached the stage where comets usually come alive. Compared with the haunting silence of Oumuamua and the relatively familiar behavior of Borisov, Atlas was blazing its own trail, telling a new story in bright, smoky letters for astronomers to decipher. Dr. Alan Fitzsimmons of Queen's University in Belfast captured the feeling of the scientific community with a vivid metaphor. He had carefully studied all three of these interstellar wanderers. It is like receiving 3 postcards, he explained, each one from a different country, written in completely different languages, yet all describing the same basic journey of travel. The image was perfect. Each object had come from the same grand road, the endless highways between the stars, but each spoke in a different voice, carried a different flavor, and left behind a different set of questions. The shapes of these visitors added yet another layer of intrigue. Oumuamua, the first, remained the strangest of all. Careful measurements of its changing brightness as it tumbled through space suggested a bizarre body, a body that was possibly 10 times longer than it was wide, like a gigantic cosmic cigar, or perhaps like a flattened shard of rock. Nothing in our solar system resembled it. It did not spin neatly on a single axis, but wobbled and tumbled chaotically, as though some violent event in its past had knocked it into a strange rotation. Even more puzzling was the fact that as it moved, it seemed to accelerate in a way that could not be explained by gravity alone. Normally, such acceleration would be due to jets of gas escaping from a comet's surface, but Oumuamua showed no signs of such activity. To this day, scientists debate what exactly caused that motion. Some suggested it might have been pushed by a thin layer of hydrogen ice sublimating invisibly. Others imagined sheets of nitrogen ice, while a few even speculated that it might be some kind of artificial sail left behind by an alien civilization. Whatever the answer, its elongated shape and unexplained acceleration made it one of the greatest puzzles in modern astronomy. 3I. Atlas, by comparison, seemed far more ordinary in its form. Careful observations of its light revealed that its nucleus was not stretched out like a shard. It was closer to spherical, with only a modest elongation, perhaps 1.5 to 2 times longer than it was wide. It rotated calmly, taking about 29 hours to complete a full spin. Nothing like the dizzying, chaotic tumble of Oumuamua. In that sense, it seemed reassuringly familiar. More like the comets humanity had studied before, though, with enough quirks to make astronomers sit up and pay close attention. 2I. Borisov fell somewhere in between. Its rotation period, estimated at 7 to 8 hours, suggested a somewhat elongated body, though not nearly as extreme as Oumuamua. It spun gently, displaying a rhythm that was easy to follow. The contrast between the three was striking. The wild tumble of Oumuamua, the steady measured spin of Atlas, and the moderate rotation of Borisov each seemed to tell a story of different origins and different pasts, as though the scars of their birthplaces and histories were etched into their movements forever. The chemical identities of these visitors revealed even deeper mysteries. Borisov's gases told a dramatic tale. In addition to ordinary water vapor and faint traces of cyanide, it released those remarkable quantities of carbon monoxide, a clear fingerprint of a birthplace far colder than anything near our sun. The proportions of its chemicals were unlike any comet native to our solar system. It was as if Borisov had carried in its body the frozen history of a star system, completely different from our own, one where conditions had allowed exotic materials to freeze and remain stable for billions of years. Atlas, on the other hand, displayed its own chemical surprises. Spectroscopic studies revealed strong signatures of silicate minerals, meaning that beneath its frosty exterior lay a rocky heart. Even more intriguing, the ratios of hydrogen, oxygen, and carbon in its gases were not the same as those found in comets closer to home. These subtle differences in isotopes told scientists that Atlas must have been born around a star with a different chemical history than our Sun. And most remarkable of all, Atlas carried complex organic molecules, chains of carbon, hydrogen, and other elements woven together into intricate structures. These compounds were shaped over millions of years, as cosmic rays bombarded the comet during its long journey through interstellar space. To think that such fragile and complex chemistry had survived across that unimaginable distance was humbling. It raised fascinating questions. How widespread might these organic building blocks be across the galaxy, and could they one day seed life elsewhere, just as similar materials may have helped spark life on Earth? Outgassing the way these objects breathed proved perhaps the most dramatic difference of all. Oumuamua famously was silent. Even when it passed closer to the Sun than Mercury, it showed no coma, no tail, nothing at all. At just a quarter of the Earth-Sun distance, where ordinary ices would have boiled away explosively, its refusal to behave like a comet inspired bold theories, from invisible exotic ices to artificial construction. It defied every expectation. Borisov, in sharp contrast, behaved exactly like the comets astronomers had studied for centuries. As it approached the Sun, it erupted in jets of gas and dust, building a long tail that glowed brightly, bright enough to be seen even through amateur telescopes on Earth. Its activity reached a peak during its closest approach, then slowly dwindled as it journeyed outward again, fading back into the cold dark as if returning home. It was the very model of cometary behavior, yet carrying with it that unusual chemical fingerprint that set it apart. Atlas once again broke the pattern. It began outgassing astonishingly early while still far from the Sun, at distances where most comets remain inert. This suggested that its body contained extremely volatile ices, substances that could sublimate even in the faint warmth of distant sunlight, or that its surface was riddled with fractures and features that made it unusually easy for gas to escape. Its coma displayed puzzling variations that could not be explained simply by solar heating, as though hidden processes within its interior were driving its activity. Atlas seemed to possess secrets deep inside it, mysteries still waiting to be uncovered. The speed at which these mysterious visitors traveled told a whole new chapter of their journeys, as if each number carried with it a secret about their past. The first of them, the strange and cigar-shaped Oumuamua, entered our solar system, racing along at about 26 kilometers every single second. To put that in perspective, in only 1 second, it could cover a distance greater than 2 times the height of Mount Everest. That kind of speed suggested that Oumuamua had not been thrown out violently, but rather had been nudged or gently pushed from its original home. Perhaps the pull of gravity from a giant planet in a nearby star system had acted like a sling, slowly setting it free into the wide and empty dark between the stars. The second traveler, Borisov, moved even faster. It swept into our neighborhood of space at around 32 kilometers every second. This higher speed hinted at a very different story of origin. Instead of being quietly nudged, it may have been flung away much more forcefully, torn out of its own system by a more violent encounter. Its pace suggested that it may have come from farther away, perhaps from a star system many light-years distant, and had been traveling across interstellar space for ages upon ages before finally arriving where we could see it. And then came Atlas, the third and wildest of the visitors. Unlike the others, it rushed into the solar system at a breathtaking speed of 61 kilometers every second. That is more than 200,000 kilometers in only 1 hour, fast enough to circle the entire Earth in less than 4 minutes. A speed so furious could not easily be explained by a simple planetary nudge. No, this hinted at something far more dramatic in its past. Perhaps Atlas had been hurled outward by a catastrophic event, a star exploding in a violent supernova, or a close, dangerous encounter with a giant black hole, or another massive object whose pull was strong enough to fling it across the galaxy. The staggering speed suggested that this object had been on the move not for thousands but for millions upon millions of years, carrying with it the scars of an ancient and extraordinary beginning. When astronomers placed the 3 travelers side by side in their minds, Oumuamua, Borisov, and Atlas, the picture that emerged was astonishing. It was no longer just about 3 strange bodies wandering into our sky. It was about what their presence meant for the galaxy at large. Their appearances together told us that the space between the stars was far busier than we had ever thought. Scientists began to realize that objects like these probably pass through the inner regions of our solar system several times in every single decade. Yet most slip by unnoticed, too faint or too small to catch even the sharpest eyes or the most sensitive telescopes. Stretching their imagination to the scale of the entire galaxy, astronomers performed calculations that left them both humbled and amazed. If 3 such objects could appear in such a short time, then there must be not just millions, not even billions, but trillions upon trillions of these wanderers, drifting across the Milky Way. Some might be giant frozen spheres of ice, as large as small planets. Others might be rocky shards left behind from collisions of worlds. Still others might be the shattered fragments of stars carried away after explosions that lit up their regions of the galaxy long ago. Each one in its own way was a traveler without a home, moving endlessly through the cold emptiness between suns. And yet, even with just 3 examples, the diversity was already striking. Oumuamua had been small and puzzling shaped, unlike anything seen before. Borisov had behaved more like a traditional comet, with a tail of gas and dust, shining faintly as it neared the sun. Atlas, on the other hand, was fast, mysterious, and possibly born of a catastrophic event. If only 3 could be so different, how much wider must the variety be among the unseen billions still roaming the galactic void? The possibilities seemed endless. Some interstellar visitors might be untouched, fossils of the earliest days of alien star systems, little samples of the very first matter formed at the dawn of time. Others might be violent debris blasted into space when planets collided, when moons shattered, or when stars tore themselves apart. Dr. Robert Werrick, the astronomer who had the rare privilege of discovering 2 of the 3 confirmed visitors, reflected on the meaning of it all with wonder. He put it in words that carried the excitement of an explorer opening a new chapter of discovery. "We've gone from 0 to 3 in less than 10 years, he said, and each one has been completely different. That means the overall population out there is far more diverse than we ever dreamed. Every single one of these objects is a traveler from another corner of the galaxy. Each carries a story of its own birth, its own journey of change, and its final exile into the endless dark." The lessons from these 3 strange wanderers were already transforming the way scientists thought about the universe. They forced us to rethink how planetary systems are born, how they grow and evolve, and how they sometimes break apart. The differences in their chemistry showed that stars across the galaxy each had their own unique histories. Like families that had lived through very different lives, their wildly different speeds showed that there was not just one way for material to be cast out of a system, but many. Some might be nudged gently by planets, others flung violently by catastrophes. Still, others hurled away in events beyond our full understanding. And perhaps the most important lesson of all was this: the arrival of such objects was not rare, it was steady, it was constant. It was part of the natural rhythm of the galaxy. The galaxy, once thought of as a silent backdrop of stars, was revealed instead as a restless living ecosystem. In this great system, matter does not remain fixed in one place. It moves, it flows, it drifts endlessly from star to star, from system to system in a ceaseless cosmic exchange. Every interstellar visitor that enters our sky brings with it a small piece of another world, a tiny fragment of another history written far away, a whisper of another time that still echoes through the darkness. As Atlas continued its bold flight toward the sun, sending back new clues, each passing day astronomers felt a shiver of excitement, a shiver that went beyond scientific curiosity. They sensed that these 3 visitors, so strange, so varied, so unexpected, were not the end of the story, but only the beginning. They were the first hints of a much larger reality. The space between the stars, once imagined as empty and silent, was in truth crowded with countless wanderers. Each one is a messenger from distant realms waiting patiently to be seen, studied, and understood. And together they form a grand chorus of travelers, slowly revealing the hidden structure of interstellar space, while also showing us where our own solar system belongs in the vast and living community of the galaxy. Enrico Fermi's famous question first echoed through scientific circles for generations. It was first spoken aloud during what seemed like nothing more than an ordinary lunch in 1950. At that table, Fermi asked a question that appeared simple but carried profound weight. If the galaxy is so vast, so ancient, and so full of stars and possibilities for life, then where is everybody? If intelligent life is not unique to Earth, then why do we not see any sign of it? For years, this puzzle was mostly a thought experiment away to spark debates about probability, distance, and technology. But once humanity began facing the startling reality of actual visitors arriving from the deep black gulfs between the stars, Fermi's old question changed. It began to sound less like speculation and more like an urgent mystery demanding fresh answers. For centuries, we had imagined the stars as unreachable points of light, separated by endless stretches of emptiness. Yet now strange objects had drifted into our solar system, objects that clearly had come from other stars. With their arrival, Fermi's question acquired a new shade of meaning. If the galaxy truly swarms with fragments, icy bodies, and wandering stones that have been flung from countless alien suns and planets, then why don't we see signs of civilizations? The civilizations that might exist around those stars. Could it be that some of these objects are not only natural debris, but also deliberate creations like machines, probes, or messengers? The original form of the Fermi paradox had always leaned heavily on one main assumption. The vast distances separating stars were so unimaginably large and so utterly empty that civilizations would have little chance of finding one another. According to this reasoning, even if millions of advanced societies were scattered throughout the Milky Way, they would remain isolated. Radio signals, no matter how powerful, would weaken and fade long before traveling across light years to another inhabited world. And as for traveling physically between stars, the resources and timescales required seem to belong more to the realm of fantasy. Even the most powerful and long-lived civilizations might struggle to send ships or artifacts across such cosmic expanses. But then the universe surprised us. Along came three visitors: Oumuamua, discovered in 2017, 2I, Borisov, discovered in 2019, and 3I, Atlas, discovered in 2025. These interstellar wanderers were not theories, not stories, but real objects moving across our skies. Their sudden appearance shattered the old picture of an empty galaxy. The void between stars was not silent, not barren, but alive with movement. It was a cosmic highway filled with steady traffic, natural couriers endlessly drifting from system to system, carrying with them the chemistry and history of distant worlds. And if nature itself could fling such messengers across the galaxy with ease, then why could not intelligent beings do the same? Why couldn't they deliberately shape objects to serve as carriers of knowledge or evidence of their existence? Astronomers, once they began running the numbers, realized the statistics were staggering. Objects larger than 100 meters in size seemed to pass through the inner solar system several times in a single decade, not once in a century. If such large visitors appeared that often, then logic demanded that smaller fragments must be arriving in even greater numbers, perhaps thousands of them every single year. Most of these tiny travelers would go unnoticed. Many would burn up in the atmosphere before ever touching the ground, leaving behind nothing but a brief streak of light. Others might be too small or too dim to detect with our current instruments. But the implication was impossible to ignore. Our world was already being sprinkled, perhaps even showered with material from other star systems on a constant basis. This revelation did something extraordinary to Fermi's old paradox. It twisted the question into an entirely new shape. The mystery was no longer simply, why do we not hear signals from other civilizations? Instead, it became, what if we are already receiving them, only in a form we do not yet recognize? Perhaps alien civilizations had been sending messages across the galaxy for thousands or even millions of years, but not in the fragile form of radio signals that fade and vanish across the void. Instead, they might be sending physical artifacts, durable messengers, designed to survive the long and dangerous journey, arriving intact in other star systems to deliver their secrets. One of the most passionate voices for this line of thought was Dr. Abraham Loeb of Harvard University. He argued that for decades, humanity had been straining its ears toward the sky, endlessly searching for radio waves. But what if the true signals were not made of soundless light in the radio spectrum at all? What if they were physical objects? A solid artifact carefully designed could hold far more information than a brief radio pulse. And unlike a signal that must be aimed and received at the right moment, an artifact would arrive with certainty. Once launched, it would cross the void on its own and deliver itself straight into another star system, carrying whatever message or knowledge its makers intended. This idea was not entirely new. Writers of science fiction had dreamed of such things for generations, filling their stories with intelligent probes and mechanical emissaries drifting through the stars. Even scientists themselves had at times imagined such devices. One famous concept was the so-called Bracewell probe, named after the scientist Ronald Bracewell, a theoretical self-replicating machine that could spread throughout the galaxy, copying itself as it went, carrying messages and sharing knowledge between civilizations. For a long time, these ideas seemed more like playful speculation than serious science. But with the sudden discovery of real interstellar objects passing through our solar system, such visions began to look far less fanciful. If every technological society at some stage of its history had launched artifacts into the dark, then the Milky Way might be filled with them, whether intentionally as beacons, as messengers, or merely as the discarded leftovers of industry. It might be teeming with silent messengers drifting patiently through space, waiting for someone to notice. The difficulty, however, was immense. How could anyone tell the difference between a natural rock ejected from a distant star system and a deliberately designed machine built by intelligence? Nature could be strange and inventive, producing bizarre shapes and motions, and distinguishing chance from intention was a puzzle of the highest order. Oumuamua, the first known interstellar visitor to enter our solar system, brought this question into sharp focus. Its appearance in the year 2017 shook astronomy to its core. Here was an object unlike any comet or asteroid we had ever seen. It had an extreme elongated shape, like a gigantic cigar or perhaps a flattened shard. It displayed a mysterious acceleration that could not be explained by gravity alone. Yet it showed no tail, no jet of gas, no cloud of dust that comets normally release when warmed by the sun. Its silence and its strangeness left scientists baffled. For some, these peculiar traits were enough to wonder aloud whether Oumuamua might actually be artificial, perhaps a creation of another civilization sent intentionally or drifting as a relic of some ancient mission. Yet the scientific community as a whole was hesitant. Science is cautious by nature, built on skepticism, and designed to resist rushing into extraordinary conclusions. The principle of Occam's razor teaches that we should prefer the simplest explanation before leaping to complex ones. To many scientists, suggesting alien technology was simply too extravagant, too speculative, without overwhelming evidence to support it. Instead, they leaned toward rare and exotic natural explanations. Perhaps Oumuamua was a fragment of frozen hydrogen, or a shard of nitrogen ice, or some other unusual but natural material never before observed. Even if these theories seemed stretched, they felt safer than making the leap to alien technology. But the discovery of more interstellar visitors began to chip away at this conservative view. The numbers did not lie. If such objects were truly rare, then the fact that humanity had discovered them so quickly in such a brief window of time seemed an almost miraculous coincidence. Barely a few decades since we'd built the instruments capable of finding them, why would we of all generations be so lucky as to catch them drifting by? Unless, of course, they were not as rare as once thought. If some of these wanderers were indeed artifacts launched by civilizations long ago, then their sudden appearance during our own era of discovery would make far more sense. The timing sharpened the question even more. In only the first 8 years of systematic searching, astronomers had identified not one, not two, but 3 interstellar objects. In all the long history of humanity stretching back tens of thousands of years, we had never knowingly seen such a visitor. And yet, as soon as our technology matured enough to look carefully, 3 of them appeared in quick succession. Was this sheer luck of staggering proportions, or was it evidence that these objects were actually common, so common that we had simply been blind to them until our telescopes grew sharp enough to notice Dr. Avi Loeb, a famous astrophysicist with a reputation for bold ideas, decided not to leave the mystery of Oumuamua entirely to speculation. He actually ran the numbers. If objects like Oumuamua were nothing more than natural wanderers, rare visitors flung from distant star systems, and if they appeared only as rarely as older models predicted, then the chances of humanity noticing one were low. Astonishingly low during the tiny sliver of time in which we had the necessary technology. The odds, according to his calculations, were about 1 in 10,000. Now, coincidences do happen, but this one seemed almost too much to swallow. The idea that out of the entire history of Earth, Oumuamua just happened to pass by in the brief window when we could actually see it with modern instruments strained belief. Loeb's calculation did not prove anything, but it suggested something startling. Perhaps it was unwise to dismiss other possibilities. Perhaps, just perhaps, we were looking not at a natural object, but at something engineered, something shaped with purpose by minds beyond our own. This thought was powerful enough to push the scientific community into action. The search for extraterrestrial intelligence began to change. No longer was it enough to simply point giant radio dishes into the sky and hope for a beacon. Now, whenever a strange visitor from the spaces between the stars arrived, radio telescopes turned their ears toward it. They scanned for any whisper of an unnatural signal. Optical observatories joined the hunt, watching the way sunlight bounced from alien surfaces. They were hoping to catch a glint that looked more like polished metal than dull rock. Even the detectors built to sense the faint ripples of space-time were considered for a new role, watching for the tremors that might reveal massive artificial structures quietly drifting through the galaxy, from black holes and neutron stars. The European Space Agency went a step further. They dared to imagine a mission unlike any before it, sending a high-speed probe racing to intercept the very next interstellar traveler that crossed our skies. Such a probe could perform a close-up investigation, searching not only for odd chemistry or strange shapes, but for clues that would change everything. Secret compartments, miniature computers, communication equipment, or even seeds and spores. Seeds that might have been launched across the galaxy as part of some ancient plan. The very thought was electrifying. What if our solar system was not just a home, but a harbor where messengers from long-lost civilizations occasionally stopped by? If evidence of such things were ever discovered, the consequences would be overwhelming. It would mean we were not merely learning about living civilizations somewhere far away, but also about those that had existed and vanished millions or even billions of years before. The Milky Way could already be filled with technological fossils, the silent remains of species that once thrived but are now gone. These drifting relics, half hidden among the stars, could be the only surviving testaments to cultures that rose and fell long before our sun itself was born. Exploring them might become the foundation of an entirely new field of science, galactic archaeology, a discipline devoted to piecing together the history of intelligence itself, not just on Earth, but across cosmic time. Yet, even as humanity dreamed of uncovering alien artifacts, we were forced to look in the mirror, because the truth was humbling. We ourselves had already begun to add to the galaxy's storehouse of interstellar debris. Our spacecraft, the Voyagers, the New Horizons probe and others, were already leaving the solar system, carrying with them plaques, golden records and information about our world. These ships would become Earth's first ambassadors to the stars, carrying greetings to whoever or whatever might one day find them. But along with these noble messengers, humanity was also leaving behind a mess. Empty rocket stages, dead satellites, shattered fragments from orbital collisions. All of this space junk might in time drift into interstellar space as well. And what impression would it leave behind future alien archaeologists should they stumble upon the wreckage might reasonably conclude something? That Earth in the 21st century was home to a careless and wasteful species, one that polluted not only its own planet, but also the heavens themselves. This realization added a heavy philosophical weight to the entire discussion. It brought us back unexpectedly to the haunting question, once asked by the Italian-born physicist Enrico Fermi in 1950. Where is everybody? For decades, this puzzle, now known as the Fermi paradox, had troubled scientists and dreamers alike. But what if the answer was not that they were absent, but that we had been blind? Perhaps extraterrestrial civilizations were not silent at all. Perhaps their messages and artifacts were already scattered all around us, disguised as ordinary interstellar rocks. The problem was not their quietness. It was our failure to recognize them. If this idea was true, then the search for extraterrestrial intelligence had to expand beyond its old boundaries. We could no longer limit ourselves to listening for radio broadcasts across the cosmos. Instead, every interstellar visitor that crossed the threshold of our solar system had to be treated as a potential message. Its shape, its path, its brightness, even its internal structure, all of these might be parts of a code waiting to be unraveled. Of course, the task of decoding such messages would not be easy. Unlike a clear radio signal, which by its very nature is designed to stand out as artificial physical artifacts might be built with camouflage in mind, they could be engineered to look like natural objects hiding in plain sight to avoid attracting unwanted attention. The boundary between what was natural and what was technological could be razor thin, so thin that our current instruments might not be good enough to tell the difference. But as new telescopes and surveys revealed more and more interstellar objects, the old paradox of silence began to bend. The question was no longer why the universe appeared so empty. The question became something deeper. Were we truly recognizing what was already before our eyes? Humanity's ancient loneliness, the fear that we were alone in the endless night, was slowly giving way to a new vision. Perhaps we were already participants in a vast and ancient network of material exchange, a cosmic web where fragments and artifacts move silently between star systems, carrying the echoes of civilizations both living and long dead. Whether these cosmic wanderers were deliberate messengers or accidental remnants remained uncertain. Perhaps some carried signals left for us to find, while others were nothing more than forgotten debris, drifting without purpose through the void. But even the possibility was enough to reshape the way we thought about science, philosophy, and our place in the universe. The famous question of Enrico Fermi, where is everybody, might not need to be asked much longer. The answer could already be here. They are not missing. They are not absent. They are here around us, passing quietly through our skies. And at long last, we're beginning to learn how to notice them. The most striking sign that the object known as 3I, Atlas, is not a native child of our solar system lies in its astonishing speed. For most members of the Sun's vast family, speed has limits. Asteroids, comets, and icy fragments born beneath the glow of our star usually remain bound to it. They are caught forever inside its powerful web of gravity. They may travel far, some even reaching the shadowy edges of the Oort cloud, many trillions of kilometers away. But they are still linked to the Sun. They never move quite fast enough to escape completely. 3I, Atlas, however, is different. This object is not quietly circling like a loyal companion. Instead, it is tearing across space with such raw power that it has already broken free of the Sun's grasp, never to return. The very motion of this wanderer tells a story. It is not a gentle drifting away like a leaf carried slowly downstream. It is the story of a violent expulsion from its original home, a dramatic ejection from another star system far beyond our own. And after that violent beginning, it has been undertaking a lonely pilgrimage through the cold, endless dark of interstellar space. Its path carries the marks of this extraordinary start like scars that whisper of the moment it was flung into exile. When astronomers first measured how fast it was moving, their sense of wonder was immediate. Even before it felt the irresistible tug of the Sun 3I, Atlas was already racing toward us with breathtaking speed. Its measured velocity, when compared directly against the Sun's position, was between 26 and 30 kilometers every single second. That is the kind of speed that defies ordinary imagination. Imagine standing on Earth and watching an object streak across the sky, moving so swiftly that in a single heartbeat it could travel the distance from one city to another. That was the pace of this interstellar guest. To truly understand how remarkable that is, one has to compare it to the speeds of ordinary comets born in our own system. Even the comets that dwell in the farthest regions out in the dim Oort cloud only manage a few kilometers per second. When they are still far from the Sun, they move slowly, creeping through space as though weighed down by invisible chains. Only when they dive closer to the Sun do they accelerate, urged forward by the star's gravity. But 3I, Atlas was already charging forward before the Sun had any chance to act upon it. That alone set it apart. The technical phrase astronomers use to describe this kind of behavior is hyperbolic excess velocity. In simpler words, it is the speed an object keeps after it has already escaped the Sun's influence. If something was born here, its velocity always ties it to an orbit. It may be long and stretched, it may carry the body far away, but eventually it circles back. 3I. Atlas, however, possesses the one feature that no native comet or asteroid has. It will not circle back. Its trajectory is open-ended. It is the footprint of a true outsider, a traveler from the far reaches of the galaxy, a traveler that merely passed through our neighborhood on its way elsewhere. It never intended to stay, and it never will. As the visitor came closer to the Sun, its speed only grew more furious. Gravity acted upon it like a hand pulling it forward, dragging it into an even faster sprint. At the point of its closest approach, called its perihelion, scientists estimate it was dashing at more than 60 kilometers per second. That is 60,000 meters every second. A velocity so great that it crossed the inner solar system in a blur like an arrow shot across the cosmic stage. In that brief, dazzling sprint, it approached, it swung around the Sun, and then it sped outward again, beginning its return to the deep dark between the stars. Once it escapes beyond the reach of the Sun's pull, its speed will fall only slightly. After that, it will settle back into its steady interstellar cruising pace. Around the same 26 to 30 kilometers per second it carried when it first appeared. Then, like a silent ship sailing an infinite ocean, it will drift onward, bound for no particular port, continuing its endless journey through the galaxy. But why does this speed matter so much? The answer lies in the way cosmic bodies gain and lose energy. Every comet or asteroid born here in the solar system is like a dancer tied to a central partner, the Sun. No matter how far it roams, it remains bound by that connection. Even the comets pushed inwards by passing stars or nudged outward by giant planets like Jupiter still obey this law. They swing in, speed up, swing out, and then begin again. Their orbits may stretch across centuries or even millions of years, but they are still loyal to the solar family. 3I. Atlas, though, dances to no such rhythm. It came bearing far more energy than anything the Sun or planets could have given it. That extra energy is the clearest proof of its foreign birth. It is like seeing a stranger walk into a crowded room with a passport from a distant land. Immediately you know they do not belong to this household. The only way such an object could gain this surplus of motion is if it had been forged in another system, a system where something powerful enough launched it outward into interstellar exile. Astronomers have pieced together a likely origin story for such wanderers. They believe most are created during the violent childhoods of planetary systems. When new stars are born, great clouds of gas and dust swirl around them, and from that chaos new planets begin to form. But these young worlds do not grow quietly. They jostle, collide, and tug at each other with their gravity. Giant planets in particular act like cosmic slingshots. When they pull on smaller icy or rocky bodies, they can fling them outward at incredible speeds. Some of those unlucky fragments crash straight into the star, burning up in its fires. Others smash against still-forming planets. But a small fraction receive the perfect slingshot that sends them hurtling away forever, breaking free of their home system's gravity. Over billions of years, untold numbers of such cosmic exiles have been launched into the galaxy. They wander alone without light or warmth, carried along by inertia through the blackness between stars. 3I. Atlas is one of those lonely travelers. Its speed is not just a clue to its birthplace. It is also a measure of its exile, proof that it was once caught in the violent games of giant planets before being cast out. The velocity of 3I, Atlas, also hints at how long it has been journeying. At a pace of between 26 and 30 kilometers every second, the distances between stars still demand patience. Patience beyond imagination. Crossing from one star system to another would take millions of years. In some cases, it might take tens of millions of years. That means 3I, Atlas, may have been wandering ever since the very beginning of its original star system, perhaps for a span of time longer than human beings have even existed as a species. Along the way, it may have brushed close to other stars each time, having its course bent ever so slightly, yet nothing ever captured it. It kept going on and on, until at last it arrived in the region we call home. The discovery of 3I, Atlas, gains even more meaning when compared to the two other interstellar visitors humanity has seen before. The first was Oumuamua, which swept through the solar system in 2017. It moved at roughly 26 kilometers per second. The second was Comet Borisov, discovered in 2019. It entered moving even faster at about 32 kilometers per second. Now 3I, Atlas, joins them as a third chapter in this unfolding story. All three share the same vital characteristic. They were outsiders moving at extraordinary speeds, unmistakable evidence that each had been cast away from its home star by powerful and violent forces. But there is also a practical consequence to such speed. It makes these objects incredibly hard to study. They do not linger. Instead, they blaze across the solar system, staying within reach of our telescopes for only a short time. At most, we have a few months to observe them before they fade into the distance, shrinking until no instrument on Earth can see them anymore. By the time astronomers are certain they are truly interstellar, the visitors are usually already leaving. In the case of 3I, Atlas astronomers were fortunate. It was spotted just before it reached its closest approach to the Sun. This gave scientists a precious, if brief, window to study it. Still, even then, it brightened and dimmed quickly, slipping away from most telescopes in less than a single year. The breathtaking velocity of 3I, Atlas, sparks yet another question. Could humanity ever hope to chase down such a visitor with a spacecraft? The honest answer, at least with the technology of today, is no. To intercept something moving at tens of kilometers per second requires staggering amounts of energy and flawless timing. The fastest probes humanity has ever built, such as the Parker Solar Probe or the Voyager spacecraft, move quickly, but they are still far slower than this interstellar messenger. Yet, the dream remains. Perhaps in some future age with propulsion systems far beyond our current rockets, humanity might one day be able to prepare years in advance and launch a mission capable of catching such a wanderer. To meet it up close would be like shaking hands with a traveler from another world. Adding to the wonder of this tale is the fact that the telescope which first detected 3I, Atlas, was not even designed to find such interstellar marvels. It was part of the Atlas survey, a system built for the very practical purpose of scanning the skies, scanning for dangerous asteroids and comets that could threaten Earth. And yet, in December of the year 2019, this humble sentinel achieved something extraordinary. It captured humanity's very first sight of an interstellar object that was bright enough to reveal itself in detail. A visitor that had crossed the gulf between the stars to momentarily pass through our solar system. The Atlas project is one of the most ambitious and fascinating achievements of modern astronomy. It is not the kind of project that builds a spacecraft to travel to other planets, nor does it rely on giant rockets that roar into the heavens. Instead, it works quietly night after night with its gaze fixed on the endless sky above. The project was created by the University of Hawaii, and its lifeblood flows from the funding provided by NASA through the Planetary Defense Coordination Office. The very name of that office tells a dramatic story, for its role is to act as Earth's guardian, watching the skies for possible dangers that may someday descend from the dark reaches of space. The mission of Atlas, when summarized in plain words, may sound disarmingly simple. It is to scan the heavens every night, searching for asteroids and comets that wander close to our planet, some of which might one day far or near pose a threat to Earth. But the importance of this work cannot be overstated. The survival of entire civilizations may one day depend on such early warnings. To carry out this noble task, Atlas depends on Special Eyes Wide-Field Schmidt telescopes. These instruments are not the largest nor the most powerful telescopes ever built by humanity. There are mirrors, far bigger observatories perched on mountain peaks that can peer more deeply into the universe. Yet the strength of Atlas's telescopes is not brute size or sheer power. Their genius lies instead in speed and efficiency. They are like watchtowers built not to look at one tiny detail with utmost precision, but to sweep the whole horizon again and again. Imagine a sentry guarding a city wall. One guard may stand still, staring far into the distance at one direction, while another may pace swiftly along the wall, scanning every angle. The Schmidt telescopes of Atlas are like that second guard, moving their gaze restlessly across vast portions of the night sky, searching for anything that shifts or moves against the still backdrop of stars. In a single glance, they can capture huge stretches of sky. This makes them perfect for the mission of quick detection. At the present time, Atlas operates with 4 such telescopes. 2 of them stand on the Hawaiian Islands, one high upon the slopes of Mauna Loa, the great mountain that rises from the sea, and another on Haleakala, the sacred peak of Maui. These 2 eyes look out over the Pacific, night after night, ever watchful. The other 2 telescopes were placed far away in the southern hemisphere, where different stars wheel across the heavens. One stands in Chile in the thin, dry air of the Andes, and the other keeps vigil in South Africa. Together, the 4 form a kind of global sentinel. Each night, these 4 eyes sweep the heavens several times over, tirelessly recording the star fields and marking any tiny point of light that dares to move. Automated systems quickly analyze the data, flagging suspicious objects that might deserve closer scrutiny. Most of the time, the moving points discovered by Atlas turn out to be nothing unexpected. They're usually ordinary asteroids from the Great Main Belt that lies between Mars and Jupiter, or comets already known from earlier visits. Yet, every so often something unusual appears, a light traveling faster than common asteroids or moving along a path unlike any seen before. It is in such moments that the excitement of discovery stirs. One of these extraordinary moments occurred on the 12th day of December in the year 2019. On that night, one of the Atlas telescopes noticed a faint and subtle visitor gliding against the black sky, moving just a little quicker than an ordinary comet. At first glance, astronomers assumed it was another icy wanderer drifting inward from the cold outskirts of our solar system. Following custom, they gave it a temporary label C 2019Y4, but as the nights went by and more telescopes around the world turned to watch this new arrival, strange details began to emerge. The path it followed through the heavens was not the usual looping orbit of a long-period comet, those icy bodies that return after journeys of tens of thousands or even millions of years. Instead, early calculations showed that this visitor traced a hyperbolic trajectory. It had an eccentricity greater than 1. To the non-specialist, this phrase may seem obscure, but to astronomers, it is a flashing signpost. For any object in our solar system bound by the gravity of the Sun, its orbit must take the shape of a circle or an ellipse. Even a long-period comet follows an elongated ellipse. A hyperbola, however, is different. It does not close upon itself. It is the mathematical shape of escape, the path of a traveler who is not bound to return. When astronomers saw this, they realized what it meant. An eccentricity greater than 1 pointed to a body not born in the solar system at all, but arriving from the great beyond, ejected from the distant nursery of another star long ago. Weeks of careful tracking confirmed this astonishing truth. This was no ordinary comet at all, but an interstellar visitor. It was only the third such traveler ever confirmed by humankind. Before it, there had been only 2. The first was the enigmatic object called Oumuamua, discovered in 2017. It puzzled astronomers with its strange cigar-like or pancake-like shape and its mysterious acceleration. The second was the Comet 2I, Borisov spotted in 2019, a far more ordinary-looking comet, but still carrying the exotic badge of interstellar origin. Now this new object was given its rightful name, 3I, Atlas, the third interstellar wanderer to grace our skies. The timing of its discovery made this moment even more precious. Oumuamua had been seen only after it had already swept past the Sun, when it was on its way out of the solar system, fading quickly into the dark. Borisov too had been discovered fairly late in its passage, but Atlas had spotted 3I, Atlas before it had reached its closest approach to the Sun. This was like meeting a traveller at the city gates rather than catching only a fleeting glimpse as they vanished down the road. It gave astronomers precious weeks of extra time to study the comet as it brightened under the Sun's warmth. Time in astronomy is an invaluable gift. With it, researchers could perform follow-up observations in detail spectroscopy, which breaks the light of the comet into its rainbow of colors, measurements of its brightness which show its spin and shape, and educated guesses about its composition and origins. The Atlas system is especially suited for such discoveries. The largest observatories on Earth are like deep-sea divers, plunging their gaze into the depths of space within a narrow field, seeing faint galaxies billions of light-years away but only in small slices of sky. Atlas, by contrast, trades depth for breadth and speed. It sweeps across the entire visible sky every 2 nights, making it the perfect net to catch fast-moving faint visitors that might otherwise slip unseen through the gaps. In this sense, Atlas acts like a farmer casting a wide net across the ocean, catching fish of all kinds, some familiar and some exotic, while the great deep-sea harpoons wait for bigger but rare game. Once Atlas raised its signal of discovery, observatories around the world leapt into coordinated action. From Hawaii, the Pan-STARRS telescopes joined the search, adding their sharper eyes. The powerful Gemini Observatory turned its mirrors toward the comet. Even the legendary Hubble Space Telescope, orbiting high above Earth, was brought to bear on this faint interstellar guest. From every continent, astronomers coordinated their work, measuring its brightness, analyzing its colors, studying the faint glow of its tail. Observations were not limited to visible light. Infrared telescopes, added their contributions, painting a fuller portrait of this cosmic traveler. Without the quick eyes of Atlas, such an international chorus of observation might never have come together in time. The discovery of 3I, Atlas, showed just how far the technology of sky scanning has advanced in only a few years. Before the year 2017, humanity had never detected any interstellar visitor. This did not mean they were absent. It meant our eyes were not sharp enough, nor our search wide enough to see them. These travelers are small, dim, and move at staggering speeds. To catch them requires a constant watch over enormous portions of the heavens. Atlas proved that with the right tools, humanity has entered a new age, an age in which the stars may send us more visitors than we ever dreamed. What once seemed an extraordinary coincidence may become a more common event, a new chapter in our understanding of the cosmos. And this is only the beginning. The future holds even greater promise. Soon, the Vera C. Rubin Observatory rising in the Chilean Andes will begin its grand project, the Legacy Survey of Space and Time. With a gigantic mirror measuring 8 4/10 meters across and a vast field of view, this observatory will scan the southern skies. It will do this every few nights. Its vision will be so deep and so wide that even fainter and more distant interstellar wanderers may be caught. If Atlas, with its modest telescopes, could discover 3I, Atlas, then Rubin's mighty eye, may open the floodgates, a flood of a whole population of interstellar messengers waiting to be found. As astronomers studied 3I, Atlas in detail, they relied on two of the most valuable tools of planetary science: the study of color and the study of reflectivity. For interstellar visitors, no spacecraft can be sent to take close-up pictures. The only information comes from the sunlight that bounces off their surfaces. Every shade of color, every flicker of brightness, carries whispers of their history. When 3I, Atlas, was first observed, it shone with a bluish-green tint. This hue is often the signature of comets rich in volatile ices. Certain gases, such as cyanogen or diatomic carbon, glow in green-blue colors when struck by sunlight. The tint suggested that the comet had been born in the frozen outer regions of some faraway star system, a place cold enough for ices to survive for billions of years. Its very color revealed its icy nature, a traveler from the cold. Further measurements showed that it reflected only a small portion of the sunlight that touched it, between 4 and 10%. This is nearly as dark as black as coal, a property shared by many comets in our own system. Astronomers call this quality low albedo. It meant that its surface was cloaked in dust, rich in carbon and other complex organic materials. Over countless millions of years, drifting through interstellar space, the comet had been bombarded by high-energy cosmic rays. These invisible bullets of radiation slowly transformed simple ices into dark, tar-like organics, leaving a reddish crust like soot. In this way, the surface became a witness to the passage of time on cosmic scales. When astronomers compared Atlas with other strange travelers that have entered our solar system from the vast darkness beyond its individuality, became even more striking. The very first such wanderer ever detected by human eyes and instruments was the mysterious object known as Oumuamua. That discovery astonished the scientific world. Oumuamua shimmered with an unusual reddish metallic glow, unlike anything astronomers were used to seeing. Many experts believe that this strange shine was the result of countless ages of exposure to the harsh and unforgiving conditions of space. For millions upon millions of years, cosmic radiation and tiny grains of interstellar dust may have bombarded its surface, changing its appearance little by little until it took on that peculiar hue. The second known visitor from the stars was a comet named Borisov. Unlike Oumuamua, Borisov appeared far more familiar to scientists. It behaved very much like the long-period comets that are born in the distant Oort cloud surrounding our own solar system. Its icy heart and dusty tail were not so different from the frozen bodies we occasionally see blazing across our skies. Borisov, in a sense, was like a cousin to the comets we already know, just one that came from another star system. Atlas, however, does not fit neatly into either category. It seems to stand somewhere in between. Like Borisov, Atlas is made up of fragile ices and volatile materials that evaporate easily when warmed by the sun. Yet at the same time, it behaves far more quietly. It does not burst out with wild plumes of gas or dramatic displays of dust. Instead, its activity is weak and subdued, as though it is holding something back. Astronomers suspect that the surface of Atlas is coated with a thick outer shell of hardened material. This crust acts like a protective blanket, slowing down the escape of gases from deep within. The lively heart of Atlas may still be there, hidden under layers of material that have been shaped and processed by time. Even the very color and faint brightness of Atlas whisper secrets about its long journey. Ordinary comets that never leave the Sun's family do not experience the same hardships. Atlas, by contrast, has endured the cold emptiness of interstellar space, where there is no warmth, no light, and no protection from invisible storms. For millions upon millions of years, it has been battered by radiation streaming across the galaxy. Microscopic meteorites have pelted its surface. Clouds of drifting dust have slowly buried and altered it. These relentless cosmic forces darkened its exterior, covering it in thin films rich in organic matter. Yet beneath that blackened skin, the ices lying deep inside have remained largely untouched. They were shielded from the endless bombardment, protected by their great depth. This is why astronomers pay so much attention to the faint jets of gas that Atlas still releases when it draws near the Sun. The fact that Atlas can still breathe out even a trickle of vapor is a powerful clue. It tells us that the inner ices are still there, still frozen, still preserved. Preserved since the moment Atlas was first cast out of its home star system. That means that within this small dark traveler, there are ancient materials older than recorded human history, pristine pieces of another planetary nursery. By using advanced tools that split sunlight into its many colors, scientists have been able to study Atlas in greater detail. These spectroscopic observations reveal the unmistakable fingerprints of water, ice, and carbon monoxide, two essential ingredients that are also found in the comets of our own solar system. But Atlas may hold these substances in different amounts than we are accustomed to. For example, if it contains much more carbon monoxide compared to water, this would suggest something. It would suggest that Atlas was born in a region unimaginably cold and distant from its parent star, perhaps even farther away than the frozen worlds of our own Kuiper belt. Such details are not minor curiosities. They are the very clues that help astronomers figure out whether Atlas formed around a star very much like our Sun, or around a cooler, dimmer red dwarf star. Even the smallest difference in its chemical recipe carries enormous meaning. Each variation speaks of the environment in which distant planetary systems are built, showing us how nature may experiment in ways different from what we see here at home. The brightness, or more precisely the reflectivity of Atlas, also acts like a cosmic clock, offering hints about how long it has been wandering between the stars. If its surface still gleamed with the dazzling brightness of fresh ice, it would suggest a recent escape, as though it had only just broken free from its birthplace. But Atlas does not shine brightly. Instead, it looks darker and more weathered, its skin aged by exposure. This tells a different story, one of ancient exile. Atlas may have been roaming for tens of millions or perhaps even billions of years. Imagine that a lonely object drifting in silence through the void, drifting for a span of time longer than the age of many mountain ranges on Earth. Its current modest reflectivity strongly supports this view. Over so many countless ages, a thick coating of carbon-rich dust has formed upon its surface. And yet, hidden beneath this darkened armor, its frozen heart remains untouched, holding secrets from another time and another place. To astronomers, the reddish tint and the scarred, mysterious surface of Atlas are not merely oddities, they are windows into faraway worlds and ancient epics. Each detail is a clue, each observation a piece of a grand puzzle. Together they help scientists trace the story of how comets, planets, and entire planetary systems are born, shaped, and transformed. Visitors like Atlas are far more than curiosities. They are messengers from the galaxy at large. Every one of them offers us a rare opportunity to peek into places we may never be able to reach. They remind us that our solar system, for all its beauty and richness, is only one small corner of an unimaginably vast universe. The arrival of each interstellar traveler carries a message that the galaxy is alive with variety, that its nurseries of creation are everywhere, and that the story of our sun and our planets is but one verse in a far greater cosmic song. The most recent spectroscopic measurements of the mysterious interstellar traveler known as 3I, Atlas, revealed something deeply unsettling. The object's isotopes, the delicate fingerprints of its atoms, showed strange ratios that did not match any process of star-born element creation that science had ever proposed. It was as if this strange visitor had been forged in conditions unlike anything ever witnessed anywhere in the known universe. The only other possibility was even more shocking. Perhaps the grand models of stellar chemistry and cosmic evolution that humanity had trusted for generations were incomplete, and they might have to be torn apart and rebuilt from the ground up. The world of science, already divided by the mounting riddles surrounding these interstellar guests, grew even more fractured. Two camps emerged, each digging in their heels. On one side stood the traditionalists, often called the methodological conservatives. They insisted on patience, reminding everyone that natural explanations must be exhausted to the very last possibility. Exhausted before anyone dared whisper about stranger, more exotic ideas. On the opposite side stood a growing chorus of bold researchers, men and women convinced that the strange puzzles piling up could no longer be brushed aside. They argued that theories once dismissed as mere science fiction had now earned the right to be considered as serious contenders for truth. The fiercest of these debates still swirled around Oumuamua, the very first interstellar visitor humanity ever detected back in 2017, 8 full years before 3I, Atlas, appeared. Even now, long after it had vanished into the dark, its bizarre features haunted astronomy. Oumuamua's oddly elongated shape, like a giant shard or a flattened pancake, and its unexplained acceleration through space refused to fit into any natural explanation. Teams of scientists across the world ran not just dozens but thousands of computer models. They simulated every possible origin they could dream of. They tested ideas such as tidal shredding near massive stars, or catastrophic collisions inside dense clusters, or the slow release of energy from exotic ices evaporating in sunlight. Yet time after time, none of these theories managed to reproduce all of Oumuamua's peculiar traits. Something about it remained elusive, beyond the reach of ordinary science. One of the most respected figures urging caution was Dr. Alan Fitzsimmons of Queen's University in Belfast. He was a veteran in the study of comets and asteroids, a man deeply rooted in the natural order of explanation. He often reminded his colleagues that the history of astronomy was full of mysteries that had once seemed to cry out for supernatural or alien answers. Answers until at last they were understood by natural means. Oumuamua may be strange, he declared firmly, but strange does not mean artificial. Those who lean toward caution clung to increasingly elaborate natural models. Perhaps they suggested Oumuamua was a block of solid hydrogen ice, evaporating so slowly that its escaping gases remained invisible. Or maybe it was a shard of frozen nitrogen once part of a planet's surface, ripped away in some ancient catastrophe and hurled into the galaxy. Both explanations required extremely rare conditions bordering on the improbable, but at least they stayed within the safety of known chemistry and physics. Yet there were voices unwilling to settle for such stretched ideas. Dr. Abraham Loeb of Harvard became the most outspoken of them all. To him, the natural explanations were so forced, so unlikely, that they seemed less believable than the far bolder possibility. The possibility that Oumuamua was a product of technology, when you must invent invisible, outgassing, unheard-of materials and processes no one has ever observed. He argued maybe it is time to admit something. Maybe we might be looking at something made, not something born. The dispute grew far larger than any one object. It blossomed into a clash of philosophies about the very heart of science itself. What was the proper burden of proof for extraordinary claims? At what point does caution become blindness? Should conservatism shield science from reckless error? Or was it in fact holding back the breakthroughs that humanity most desperately needed? Some tried to walk a middle road. Dr. Michelle Bannister of the University of Canterbury reminded everyone that the true question was not whether a specific interstellar visitor was natural or artificial. Instead, she argued, the greater lesson was that humanity's understanding of how planets form, how stars evolve, and how matter behaves in interstellar space was still painfully incomplete. Whether the answer lies in bizarre natural processes or in alien design, she said, one thing is certain: we are missing something very important. The tension only sharpened when the media seized on the story. Headlines screamed about alien probes and messengers from the stars, whipping public imagination into a frenzy. This forced many scientists to retreat into defensive positions. They leaned hard on conventional explanations, not always because they truly believed them, but because they feared being accused of chasing sensationalism. In private, some even admitted they avoided mentioning artificial possibilities. They were terrified that a careless word could destroy their reputations. There were echoes of history in all this. When pulsars were first discovered in the late 1960s, their astonishingly regular radio pulses baffled astronomers. At first, no natural cause seemed possible, so the signals were jokingly called little green men. Only later did scientists realize these signals came from an entirely new kind of star, a rapidly spinning neutron star, not extraterrestrial life. But the interstellar visitor debate was far harder to solve. Pulsars could be studied again and again for decades, but objects like Oumuamua flashed past only once. They swept through the solar system in a few fleeting weeks before vanishing forever into the darkness. That tiny window left astronomers with nothing but fragments of data, no second chances, and no way to truly settle the matter. Even the very culture of science itself began to work against solving the puzzle. Peer review rewarded safe, incremental findings over daring leaps. Funding committees hesitated to back risky projects. Careers advanced more smoothly by polishing old models than by tearing them down. Younger scientists often felt cornered. Their most thrilling ideas involved bold, unconventional thinking, but pursuing them could ruin their reputations before their careers had even taken flight. Dr. Jennifer Bergner of the University of California, Berkeley, spoke of this pressure openly. I have seen young faculty silence their own ideas because they are afraid of being branded as fringe thinkers, she said. We are building a culture where the most important questions cannot even be asked aloud because asking them might end a career. The global nature of science only added to the friction. Cultural traditions shaped how different regions approached the question. Many European scientists leaned heavily on caution and restraint. Americans tended to be more willing to speculate out loud about daring possibilities. Asian researchers often served as a balancing force between these extremes. On social media, however, the divisions exploded. A single short thread on Twitter suggesting that Oumuamua might be an alien probe could spread to thousands of readers in hours, while careful, detailed research papers arguing for natural models went largely ignored outside academic circles. This polarization even reached into telescope time allocation committees. Researchers proposing to search for natural explanations found themselves competing directly with those daring to look for signs of technology. The committees, in effect, were forced to choose not only which objects deserved precious observation time, but which philosophy of science they would fund. Some research institutions quietly began following unwritten rules. They avoided giving money to projects openly searching for alien technology. They preferred instead to support work that would always yield publishable, respectable results. Yet beneath this practical stance lay a deeper generational divide. Older established scientists often resisted ideas that threatened to unravel decades of their life's work. Those whose reputations rested on the stability of existing models. To accept radical new interpretations meant risking everything they had built. Younger scientists, on the other hand, had less invested in tradition. They were freer to imagine revolutionary possibilities, to entertain ideas their mentors dismissed as dangerous. Caught between these camps was Dr. Robert Werrick, the astronomer who had first discovered both Oumuamua and later 3I, Atlas. He admitted that the discoveries had unsettled him. When you spend your whole career looking for ordinary asteroids and comets, he explained, and then suddenly stumble across objects that fit none of the categories, it forces you to question everything you thought you knew about the solar system. As more and more interstellar objects were discovered, each one brought new puzzles, new limits, and new contradictions. Theories once considered solid grew weaker as they were stretched to fit the facts. The more scientists tried to force natural explanations onto these objects' bizarre properties, the less convincing those explanations became. At the same time, the same data could be interpreted in an astonishingly different way, as evidence that the galaxy might hold not just random debris, but a population of crafted artifacts, each built with some unknown purpose in mind. Perhaps the most important transformation, however, was not in the data but in the scientists themselves. The community was being forced to confront its own hidden assumptions. Assumptions about what counted as reasonable, about what was too bold to consider, about the fine line between science and speculation. That line, once thought sharp and clear, was becoming blurred. Exotic natural processes and artificial technology no longer sat neatly on opposite sides of a divide. Instead, they tangled together in the same uneasy space, leaving humanity with a single, undeniable truth: the universe was stranger than anyone had dared to imagine. When the official talks of international astronomy conferences had ended, strange and daring questions began to surface, and only the most restless minds remained in quiet conversations. Questions that just 10 years earlier would have been dismissed with laughter or waved away as science fiction. People now asked each other in hushed but excited tones, if humanity ever truly stumbled upon alien technology, how would we even recognize it? What kind of marks or signals would make it clear beyond doubt that an object was not a natural fragment of rock or ice, but something carefully shaped and sent by intelligence? And then came the most haunting question of all, one that sent shivers through even the most rational scientists. If undeniable proof of extraterrestrial intelligence ever arrived, how should the scientific world, indeed, how should humanity itself respond? These were no longer idle speculations or playful questions thrown around to pass the time. The situation had changed. With powerful survey telescopes now scanning the skies each night, new visitors from beyond the solar system were being discovered more frequently. Each detection forced astronomers to wrestle with data that touched the deepest foundations of their knowledge. Knowledge about how matter forms and behaves, how planetary systems are born and die, and even about where humankind truly fits within the vast and mysterious universe. The arguments that unfolded around these strange interstellar travelers revealed more than just scientific puzzles. They uncovered something far more human, an uneasiness with the unknown. Were these bizarre readings and unusual features simply the result of exotic physics that we had not yet learned to understand? Or could they truly be the fingerprints of civilizations so distant and advanced that their creations wandered between the stars? Either possibility carried with it a breathtaking implication. Slowly, a single truth was emerging, impossible to ignore. The universe was not the neat, well-ordered clockwork that earlier generations had imagined. Instead, it was a wild, surprising, and endlessly rich place, full of wonders that challenged even the boldest ideas of the past. The debates carried on, sometimes calmly and sometimes with fiery passion. In laboratories, lecture halls, and conference rooms scattered across every continent. Yet, while human voices rose and clashed over these questions, the objects themselves continued on their quiet journeys. They drifted silently through the deep black of space, following ancient courses laid down perhaps millions or even billions of years ago, indifferent to the quarrels of a young and curious species. Each one carried secrets within it, secrets that humanity was only just beginning to develop the tools, the imagination, and the courage to uncover. The future of discovering travelers from other star systems was arriving far sooner than anyone had dared to expect. High in the thin mountain air of the Chilean Andes, the Vera Sea, Rubin Observatory was completing its final tests. There, in one of the most remote and breathtaking landscapes on Earth, months ahead of schedule, the work had been sped up by a sense of urgency because the universe was not waiting. Cosmic visitors were already slipping through our solar system one after another, and humanity had no choice but to build the tools needed to find them. This remarkable facility, once fully awake and operating, promised to completely change the way humanity searched for and studied wanderers. Wanderers from the distant realms of the galaxy. At the very heart of the observatory stood two extraordinary instruments working together like the eye of a giant. The first was a vast mirror, more than 8 meters wide, polished to perfection to catch the faintest glimmers of starlight. The second was a camera of almost unbelievable power, containing more than 3 billion tiny light detectors or pixels, each one ready to capture the secrets of the night sky. Together, these instruments would sweep across the heavens, scanning the entire visible sky once every 3 days. Each night, they would gather around 20 terabytes of fresh information, enough data to fill thousands of modern laptops. Even more astonishing, the observatory would be able to detect light as faint as the 24th magnitude, roughly 40 million times dimmer than the faintest star that the human eye can see unaided. Dr. Mario Juric, the scientist in charge of the observatory's advanced data systems, described just how revolutionary this would be. "We are moving from discovering maybe a single interstellar visitor in an entire decade," he explained, to perhaps discovering dozens within a single year. And instead of scrambling to study them as they rush out of the solar system, we will watch them from the very instant they appear. Until this moment, astronomers had been forced to depend largely on luck. A visitor from another star had to pass close to Earth, and it had to shine brightly enough for older telescopes to even notice it. That meant most of them slipped by unseen, like shadows passing in the night. The Rubin Observatory would change this completely. Its sweeping gaze would widen the search net across the sky, catching faint travelers as they entered the inner solar system. and giving scientists not just days but sometimes months or even years of advance notice. Notice before these objects came nearest to Earth. But spotting these wandering guests was only the beginning. The true revolution would come not from a single detection, but from the ability to study hundreds or even thousands of them. By comparing, so many scientists could begin to see patterns hidden within the chaos. They could learn whether most of these visitors came from young star systems or ancient ones, whether they were mostly icy like comets or rocky like asteroids, and what powerful forces had flung them away from the stars where they were born. Questions that had haunted astronomy for decades about the origins, the composition, and the journeys of these messengers might finally be answered. To make sense of the flood of information, scientists were training artificial intelligence systems. Every single night, the Rubin Observatory would track billions of moving objects across the sky. But within that overwhelming sea of motion, special machine learning programs would be able to recognize the subtle fingerprints of a true interstellar traveler. In only a few hours after discovery, computers could raise a red flag and announce, "Here is a likely visitor from another sun." The work would not stop there. The European Space Agency was preparing companion systems to ensure that once a candidate was found, telescopes around the globe could quickly take a closer look. Within mere minutes of confirmation, observatories on several continents would turn their mirrors to the target, measuring its spectrum, spin, shape, and color before it faded again into the cosmic dark. Meanwhile, across the ocean, NASA's Jet Propulsion Laboratory had already gone further. Designing rapid response spacecraft meant to intercept the most intriguing visitors. These spacecraft concepts were bold, relying on solar sails as vast as football fields, and on daring gravitational slingshot maneuvers around planets to reach astonishing speeds. They would have to, because some of these visitors moved at dozens of kilometers per second, racing through the solar system faster than anything humanity had ever attempted to chase. Dr. Julie Castillo-Roges, the scientist leading these spacecraft studies, explained the scale of the challenge. "We are talking about chasing down objects moving faster than anything we have ever intercepted. The spacecraft cannot simply launch when a target appears. They must be placed in waiting in special orbits, ready to strike at the right moment. And when the time comes, the maneuvers must be perfect, with almost no room for mistakes." The potential rewards, however, were worth every risk. To intercept and sample even a single interstellar object could change everything. Small fragments collected and returned to Earth might reveal the true conditions of their birth, and scars left by millions of years of cosmic radiation. And perhaps, though still only a thrilling speculation, the faint chemical traces of life from another world. Yet there was an even more astonishing possibility: the discovery of something that nature alone could not explain. If even a fraction of these visitors were artificial, if they were probes or artifacts left by other civilizations, then a wide and constant survey like Rubin's would eventually find them. No longer would humanity be left debating a single strange case like Oumuamua for years on end. Instead, patterns would emerge. Clear, repeated evidence could reveal the presence of extraterrestrial technology beyond any reasonable doubt. To prepare for such possibilities, scientists were expanding their search beyond ordinary visible light. Radio telescopes were already being programmed to automatically scan interstellar visitors for deliberate signals, building on decades of techniques pioneered by the Search for Extraterrestrial Intelligence, or SETI. Infrared observatories in space would search for unusual heat signatures, perhaps betraying hidden engines or exotic materials. The James Webb Space Telescope had already proven its astonishing ability to study the faint light of distant solar system objects, and its methods could easily be extended to interstellar travelers. Even wilder ideas were being discussed. Gravitational wave observatories designed to feel the trembling fabric of spacetime might one day pick up the presence of unusually massive interstellar bodies. Neutrino detectors sensitive to ghost-like particles that barely touch matter could perhaps spot visitors carrying radioactive elements, or even artificial reactors inside them. The consequences stretched far beyond curiosity. Planetary defense, once thought to deal only with asteroids born in our own solar system, had to expand its scope. While the chance of an interstellar body striking Earth in any given year was extremely low, new studies showed they were far more common than anyone had guessed. Models suggested that catastrophic impacts from such objects might occur once every few million years. That may sound rare, but in the deep history of Earth, it was frequent enough to have shaped the path of life itself. The unsettling thought that an artificial object could someday arrive deliberately aimed at Earth was enough to spur serious global discussions. Even if still just speculation, governments were already drafting new policies. If a discovered object ever showed signs that were unmistakably artificial, international consultations would begin immediately, much like the procedures that already existed for asteroid threats. But in this case, the stakes would be even higher, for humanity might be on the verge of its first encounter with another intelligence. Universities too were adapting to this dawning reality. Entire graduate programs were springing up around the study of interstellar visitors. Students were being trained in astronomy, planetary science, astrobiology, and material science. But they were also learning fields as unexpected as archaeology, because one day those skills might be needed to study artifacts not of human origin, but of civilizations born under alien suns. International cooperation was no longer just an idea spoken of at conferences. It was becoming reality at a breathtaking pace. The great powers of space exploration were moving closer together in ways that only a decade earlier would have seemed impossible. The National Aeronautics and Space Administration of the United States, the European Space Agency, Japan's JAXA, and several others were no longer working in isolation. Instead, they were weaving their missions together like threads in a vast tapestry, making sure that no part of the sky and no fleeting visitor from the stars would escape human notice. Agreements were carefully written so that discoveries and raw data would be shared freely, not locked away, and so that these wanderers from beyond our solar system would be treated as treasures belonging to all of humankind, not as prizes to be hoarded by individual nations. Even the rising giants of the private space industry were stepping into this shared effort. Companies announced bold plans for specialized spacecraft designed not just to orbit Earth or ferry supplies, but to chase down these mysterious travelers and study them up close. No one could say with certainty whether there would be any direct commercial profit to be gained from such missions. Yet that hardly mattered. The prestige of making history, the thrill of grappling with such a daunting technical challenge, and the chance to push human technology to its limits, all proved more than enough to attract investors and ignite imagination. But cooperation and technology were not the only questions on the table. There was also the matter of law, a murky and uncharted ocean that humanity was only just beginning to sail. Who, for instance, would own an artifact that had crossed the gulf of light years to reach us? If such an object carried risks, chemical, biological, or even technological, who would bear responsibility for keeping the world safe? The legal puzzles were as strange and unfamiliar as the interstellar visitors themselves, and for the moment, no clear answers existed. The Rubin Observatory, high in the mountains of Chile, symbolized this turning point better than any other creation of human hands. It was not merely another telescope among many. It was a doorway, a threshold into a new era. With its immense eye scanning the skies, humanity would no longer wait passively for the universe to send chance messengers drifting into view. Instead, we would greet them knowingly, ready to meet them as they came, determined to learn their secrets and prepared perhaps to confront the unimaginable. The international space treaties that had guided human exploration until now had been written in a far more innocent time. An age when the stars were believed to be impossibly distant, unreachable places of mystery. Those old laws had not even imagined that dust stones or perhaps even machines might one day cross the void and fall into our possession. And so suddenly, new questions arose that carried with them both wonder and unease. If fragments from another solar system were recovered, who would hold the right of ownership? Could a single nation lay claim, or would such objects belong to all humanity as a common inheritance? What rules should govern their handling, especially if they contained dangerous unknown substances or carried hidden risks? And beyond even these puzzles lay the most dramatic possibility of all. What if something artificial were found? What if a probe or fragment of technology made not by us, but by another intelligence appeared among the stars and was caught by our instruments? Who then would take responsibility for its study, for its protection, for deciding whether its secrets should be shared with the world or kept hidden? Across the globe, legal scholars, diplomats, and policymakers were working frantically to shape new frameworks, a system of rules that some had begun to call interstellar visitor governance. Yet, even as they drafted proposals and debated definitions, there was an uneasy recognition among them all. The law would always lag behind discovery. It would forever be like a shadow chasing a figure that moves too quickly to be caught. And so the challenge was not only legal, it was cultural, emotional, and philosophical. Humanity's very first confirmed meeting with matter from another star had already shattered the comforting belief that we were safely isolated in a quiet corner of the cosmos. If more such visitors were found, and many scientists believed it was only a matter of time, the consequences would reshape our understanding of ourselves and our place in the universe. The possibilities were breathtaking but also unsettling. If one day evidence showed that some of these visitors were not natural fragments but the work of intelligent beings, the shock would be profound. Religious leaders began to ask how such a discovery would reshape faith. Philosophers debated whether human uniqueness was an illusion. Cultural thinkers wondered how societies might change if intelligence were no longer seen as a rare miracle, but as a repeating pattern written into the fabric of the universe itself. Even lifeless shards of alien technology, drifting silently through interstellar space, would carry with them a message of staggering importance: that other minds had once existed, that we were not the first and perhaps not the last to awaken to consciousness. They would be messengers across the void, whispering that our story was but one among countless others. No civilization in all of human history had ever faced such a moment, and the psychological consequences were impossible to fully predict. Meanwhile, the great survey telescopes of Earth went on with their nightly vigils. Their lenses swept the heavens, searching for faint streaks of light that revealed the passing of interstellar travelers. Among scientists, the mood was quiet but electric, a charged anticipation that was almost impossible to describe. The next discovery might come in a matter of months, or it might take many years, but few doubted that more were already on their way. The universe had shown itself to be far more restless, dynamic, and interconnected than previous generations had ever dared to imagine. The true question then was no longer whether more visitors would arrive, but what secrets they would bring with them. Each one held the possibility of rewriting our understanding of how planets form and how life spreads across the galaxy, and whether intelligence is a singular event or a melody that echoes again and again across countless worlds. And so, at a speed of nearly 50 kilometers every single second, the future itself was rushing toward us, bringing with it answers to questions we were only just learning to ask, and perhaps truths we were not yet ready to face. The universe is never truly silent. Even in the quietest hours of the night, when you're lying in bed and beginning to drift into sleep, a hidden orchestra of activity continues, far above you, Across 6 of Earth's continents, a vast network of robotic telescopes tirelessly sweeps the heavens. These mechanical watchers do not rest, do not blink, and do not grow weary. They are designed to notice what the human eye could never see. Every second they gather tiny streams of light packets called photons. Photons that left their stars millions upon millions of years ago. Some of those journeys began long before our species even took its first steps on Earth. And, scattered among those ancient rays, hidden like whispers in the dark, are tiny shifts in light, like faint signals of something extraordinary, small changes in position that may betray the presence of wanderers not born in our solar system. These cosmic visitors are not hurried and they are not new. They have been traveling since before Earth had oceans, since before mountains rose from its crust, since before the very sun itself had finished forming. They have crossed gulfs of black space for billions of years, indifferent to whether or not we fragile and brief creatures of flesh would ever notice them. For most of human history, we never did. Our ancestors saw the stars as fixed lights in an unchanging dome, beautiful but unmoving. Yet everything changed when one day, only a few years ago, astronomers realized something very different was happening. A stranger had entered our cosmic neighborhood, an object that was not bound by the gravity of our sun, one that had come from far away. That first realization was a shock. Suddenly the heavens no longer seemed distant and passive. They were alive, with movement, with arrivals and departures, with encounters written across spans of time and space. Encounters that made human lifetimes look like brief sparks in the dark. From that first discovery forward, more than 8 years of heated debates, passionate arguments, and painstaking research have unfolded. And from all of that work, one truth has become undeniable. The universe is far stranger, far wilder, and far less predictable than we once imagined. What once looked like emptiness between the stars is now revealed to be a kind of interstellar highway. Invisible lanes stretch between solar systems, carrying travelers across the galaxy. These wanderers are not myth or imagination. They are real, solid, ancient, and humanity has already confirmed the arrival of 3 such visitors. The first was given the Hawaiian name Oumuamua, meaning a messenger from afar arriving first. Its appearance baffled the scientific community. It was shaped not like the round comets and asteroids we're used to, but long and stretched, almost like a shard or a flattened slab of stone. Stranger still, it did not behave as expected. As it tumbled through space, its speed subtly increased, as though it was being pushed by something unseen. It gave no sign of a comet-like tail, no outpouring of gas that could explain its motion. It simply slid past, silent, mysterious, and forever unforgettable. The second was 2I, Borisov, named after the amateur astronomer who spotted it. At first glance, this one seemed easier to understand. It looked like a comet with a glowing tail of gas and dust. But closer study revealed that even Borisov carried secrets. Its gases were chemically unlike anything seen in comets of our own solar system. It bore the unmistakable mark of a different home, a birthplace orbiting some alien star we will never visit. And now, a third traveler has come into view, 3I, Atlas. With each passing day, it draws nearer, shining brighter, and offering us not only the chance for new discoveries, but also the certainty of deeper mysteries. Each of these visitors has been like a teacher, stretching the boundaries of what we thought possible, and showing us that the galaxy is not quiet or still, but alive and interconnected. Mathematics now deepens this picture even further. If in only a handful of years we have found 3 confirmed interstellar objects, then reason suggests they are not rare. In fact, calculations reveal that dozens upon dozens must pass through our solar system every single year. Most remain unseen, slipping by too small, too dark, or at angles our telescopes cannot catch. But they are there. Each one is a messenger carrying fragments from alien star systems, preserving relics of cosmic events long past, and holding clues to the violent forces that scatter matter across the galaxy. This realization transforms the way we see ourselves. Earth is not an isolated island sealed away in a void. Our planet, and indeed our entire solar system, is part of a larger cosmic network. For billions of years, fragments from other stars have been drifting here, brushing past us, sometimes even striking our world. The very materials from which Earth formed may themselves be a patchwork of dust and rock. Dust and rock born in many different stellar nurseries, scattered through the spiral arms of the Milky Way. The consequences of this new view ripple across every field of science. Planetary scientists must now reimagine the process of planet building, including the constant rain of foreign matter that arrives from deep space. Biologists studying the origins of life must confront the possibility that the building blocks of biology may not have been created solely on Earth. The first organic molecules, they may have formed in the atmospheres of long-dead stars on alien comets or within cold interstellar clouds, only to drift for millions of years before falling onto our young world. Even the grand history of our solar system may have been altered by these encounters, with the energy and momentum of passing objects nudging planets or stirring up belts of asteroids. And yet beyond the scientific implications lies a deeper and more unsettling question, one tied to the famous puzzle known as the Fermi paradox. If the galaxy is so vast, so ancient, and so filled with stars, why do we see no clear evidence of other civilizations? Why is the universe so apparently silent? But perhaps the silence is an illusion. Perhaps the void between the stars is not empty at all. Perhaps it is filled with messengers, physical objects, not fleeting beams of radio waves, objects that carry information across the ages. Civilizations, if they exist, might choose to communicate not with signals that fade in moments, but with sturdy artifacts designed to endure journeys lasting millions of years. The controversy over Oumuamua's possibly artificial nature revealed how unprepared we are to face such questions. Was it a natural shard of rock shaped and accelerated by forces we do not yet understand, or could it have been something more, a fragment of technology worn down by eons of travel? The line between natural and artificial may be thinner than we imagine. Our instruments are built to study comets and asteroids, not alien probes disguised as stones. What if such artifacts have already visited us, and we simply did not recognize them for what they were? Science, however, does not remain still. Once unthinkable ideas are becoming serious subjects of research. Funding agencies are now supporting projects that focus on interstellar visitors. Engineers are designing telescopes built to notice them. International teams are drafting protocols for how humanity should respond when the next unusual object arrives. A technological revolution is unfolding before our eyes. One of the brightest examples of this revolution is the Vera C. Rubin Observatory rising high in the mountains of Chile. When it begins operations, it will scan the entire visible sky every few nights. It will capture more data than any observatory before it. Astronomers expect that instead of discovering one or two interstellar objects every decade, they will find dozens each year. Artificial intelligence will comb through the data in hours, flagging candidates for immediate follow-up. For the first time in history, studying objects from other stars will no longer be a matter of luck, but a routine part of astronomy. This shift is not only scientific but cultural. For centuries, humanity thought of itself as living in a quiet, protected corner of the universe. We imagined that the stars were far away, unreachable and separate, but that illusion is crumbling. When Oumuamua first appeared, it caused a storm of media excitement, a wave of fascination and speculation. By the time 3I Atlas approached, the public was calmer. Yet scientists were more eager than ever. Slowly, we are learning to live with this new reality. Our solar system is not sealed, not isolated, but open to the galaxy.